I request Sridhar. Sridhar, sir is on another device. You please unmute that device. Sir is having two. I request our technical operator. Please check. Sir is on another device. Not at Sridhar. Both. Yeah, now got it. Sir, now it's ready.
Yeah, madam. So, very good morning, madam, and sir, for giving a introduction about me. And in fact, I'm very happy to join this session. And on behalf of the management and the staff of the Delhi College of Pharmacy and Research Center, where I work, I extend my wholehearted congratulations for having organized such a wonderful seminar covering the entire aspect of the spectral analysis, right from NMR, mass, and IR. So with this small introduction, I hope I can directly get into my presentation.
Welcome, sir.
Thank you, madam. Madam, can you please ask him to enable my screen sharing to screen share?
Yes, sir, we have given the access. Please open the PPT.
Okay. Okay, thank you, madam. Thank you.
Yeah, carry on. Yes, sir.
Just a minute. Okay. Hope all are able to see the presentation slide. Am I right, madam? Okay.
Yeah.
So, the topic of today's presentation is the modern methods of solving the vibrational problems in IR spectroscopy. So the topics which will be touched upon in today's session, a small introduction regarding the topic before we directly go on with the interpretation part. I mean, the electromagnetic spectrum, molecular vibrations, the theory of IR absorption, what are the factors that affects the vibrational frequency, what really we should be looking in for, or is the entire spectrum useful for us? Then we finally go with the interpretation part, and we will try to see some problems wherein I will try to give some problems, and I will request all the participants to attempt from your side to solve it. So, as all of us know, this is the complete span of electromagnetic radiations that you have in the electromagnetic spectrum. And it is this region that comes between the visible and the microwave region, which we call as the infrared radiation. And again, in this, it is a very limited region between 2.5 to 15 micrometer, which is useful for an organic chemist to interpret the structure of a compound from the IR spectrum. I think yesterday's speaker highlighted this particular slide wherein he was telling what different types of radiations does to a molecule. So we are coming to this particular part of the spectrum, wherein the molecule can undergo excitation in the vibrational level. So it is a low energy radiation, whereas the top, whatever electromagnetic radiations that you have, sometimes they're ionizing radiations and they're harmful to the body. And in certain cases, they don't knock the electrons completely out of the molecule. Instead, they excite the electrons from a lower energy level to a higher energy level. And next we have the infrared radiations, which is useful for the elucidation of a molecule, structure of a molecule. And finally, we have the radio waves, which obviously you will be seeing in the next part of the seminar, where you, with the help of identifying the spins of the nucleus, also you will be able to elucidate the structure of the compound. So we are coming to this particular aspect of the spectrum. See here. Here, what I have shown in the slide are two different compounds. If you take two different compounds, in the sense, both are alkenes, but one has got an unbranched side chain, whereas in the another one, you have got a branched side chain. You can see an isopropyl group over here. I think all the participants can look into the cursor, what I'm keeping on the slide, so that you will be able to follow which part of the slide I am focusing on. I hope all of you are able to see my cursor.
Yes, sir. Yes, sir.
Thank you, madam. So it is the isopropyl group here, and it is a straight chain group here. So obviously, when you see this particular spectrum, especially this region that comes between 1400 to 1600 region of the spectrum, you can see that the two spectrums are in fact totally different. Here you get some additional bands, you don't get those bands. Similarly, intensities are different. So everything is different between the two spectrums. You can directly, by observing the IR spectrum, you can see that you have got the spectrum for two different compounds. You can very well say that. But even when we say that, if you closely watch this particular spectrum, you can observe there are certain similarities between the two spectrums. You look into these areas, the band what you get between 1640 to 1667 centimeter inverse, it is there in the case of 1-decene as well as in the case of 4-methyl-1-pentene. And similarly, the band that you are getting here, the band that comes between 905 to 915 and 985 to 995. These two bands, what you get in the case of 1-decene, you get also in the case of 4-methyl-1-pentene. So this is the significance of IR spectrum. So I would like to say that no two compounds, never any two compounds except the enantiomers. That means if you take a compound, let us consider the optical isomer of it. One is dextroform and the levoform. Obviously, these two compounds will show the similar IR spectrum. But if you have even a minute difference between the two compounds, then definitely the two compounds will show different IR spectrum. But even then, certain IR absorption at some point of the spectrum, in certain regions of the IR spectrum, you can see similar IR absorption bands. For example, as I told you, between 1640 to 1667 and 900 to 905 and 985 to 995, you get similar bands in 1-decene as well as in case of 4-methyl-1-pentene. It is the persistence of these bands which helps an organic chemist to identify the structure of the organic compound. I will repeat, it is the repetition or it is the presence of these similar bands in both the spectrums that helps an organic chemist to identify the structure of the organic compound, in fact. So here, why it happens? Why in both the IR spectrums you are getting similar structure? Because here you have a structural similarity between the two compounds. In both the cases, if you take, it is a vinyl alkene what you're having. There is only one substitution, mono substitution. So the C double bond C, what you get here, and the C double bond C that you get in the case of 4-methyl-1-pentene, both are similar. That is why you get same type of band here. And not only that, it, as I told you, it is a vinyl group. Only one substitution is there. It is a mono substituted alkene. Here also it is a mono substituted alkene. Forget about the branching and all, but you will say that definitely only it is a mono substituted alkene. So for mono substituted alkene, you can see here the carbon hydrogen bond. This carbon hydrogen bond will show a bending vibration, which you call it as the out of plane bending vibration at two wave numbers. I mean 905 to 915, 985 to 995. In this case also, since there also you are having mono substituted alkene, the CH bending vibration will remain the same. You will get a similar band between 905 to 915 and 985 to 995. So this is the similarity between the two IR spectrum. So what I want to tell you is, whenever you take a particular molecule, there will be certain structural features which are present within the molecule that enables the molecule to exhibit a characteristic type of the spectrum or a characteristic type of the IR absorption band, using which you will definitely get an idea regarding the structure of the molecule. What and all does it reveal? The type of the double bond, whether it is aliphatic, whether it is aromatic. If the carbonyl group is present, what could be the functional group? A lot of information it gives you. So for the preliminary analysis of a molecule, it's a very useful and a powerful technique. I hope I'm audible to all the participants.
Yes, sir. Yes,
My
sir.
slide is also clear. Okay, fine. Thank
Yeah.
you. So all that bands that results in the IR spectrum, it majorly happens due to two aspects of the molecule. One is the stretching vibration and another one is the bending vibration. All those IR absorption bands that you get in a in an IR spectrum, it is only due to these two aspects of the molecule. One, that is the stretching vibration, and another one is the bending vibration. So I hope the types of stretching vibration, the types of bending vibration, I think I will make use of another animation, and then it can be more clear to you, I feel. So just a minute. Okay. I hope all of you are able to watch this animation of the different stretching and the bending that happens within a molecule. So the center, yellow colored one, it represents carbon, and these two represents the hydrogen. See what is happening in case of stretching. The interatomic distance between the carbon and hydrogen is changing in these two cases. In both the cases, the interatomic distance between the carbon and hydrogen is changing. That is what broadly you call it as a stretching vibration. And what is happening here? The interatomic distance between the carbon and hydrogen in these four structures, they are not changing. But what is changing over there? The bond angle is changing. So whenever the bond angle changes, the vibration which results from a change in the bond angle, you call them as bending vibrations. And those vibrations that results from a distance, a difference in the interatomic distance between the two atoms, you call them as stretching vibrations. Further, you can divide the stretching vibration into two types. One, you call it as the symmetrical stretching, and another one, you call it as the anti-symmetrical stretching, or in short, you call it as an asymmetrical stretching. So what is happening in a symmetrical stretching? Both the atoms move out, come back together. Both the atoms move out, come back together. At a time, if you see, the distance between the carbon and hydrogen in both the cases will be the same. Whereas in case of anti-symmetrical, what you see is, in one case it will be lengthier, in another case it will be shorter. That is what you see in the case of an asymmetrical stretching. And always this asymmetrical stretching requires more energy, or it will always occur at a higher frequency when compared with that of a symmetrical stretching. So this is about stretching vibrations. When you come to the bending vibrations, you have four types. One, you call it scissoring. What happens in case of scissoring? The two hydrogen atoms are moving in the opposite direction. In rocking, the two atoms will be moving in the same direction. In wagging, both of these hydrogen atoms are focused towards you. They come towards you. Twisting, one is moving back, one is coming to the front. So these two, you call it, that is the wagging and twisting, you call them as out of plane bending vibrations. What do you call it as out of plane bending vibrations? Here you can see that the carbon atom will be in one plane, whereas the two hydrogen atoms are in different planes. So in fact, the wagging and twisting vibrations, you call them as out of plane bending vibrations. So generally, when you take any of the textbooks, they would have given out of the plane bending vibration. In fact, they don't say that much also. They just put OOP. OOP. OOP means what? Out of plane bending vibrations. And these two, you call it as the scissoring and rocking, you call them as in-plane bending vibrations. Why do you call them as in-plane bending vibrations? Because all the three atoms are in one plane. And here you call it as, what is the difference between these two? You call this as in phase. Why do you call it as in phase? Because the two hydrogen atoms are in phase. Both of them are increasing as well as decreasing their distance simultaneously. Whereas in this case, you call it as out of phase stretching vibrations, because one is increasing, another one is decreasing. That is what. So these are the different way, because these terms sometimes create confusions in us. So we should know exactly what each term means. Though this is in phase, this is out of phase, and all these are bending vibrations. Again, you can classify them into in-plane bending, because these two are in plane because all the atoms are in one plane. These two, you call it as out of plane because the atoms are in different plane. And always remember that an asymmetrical stretching vibration always requires higher energy, or it will always occur at a higher frequency when compared with that of symmetrical stretching. And in general, when you take the stretching and bending vibration, it is easy for us to change the bond angle. So bending vibration will always occur at a lower wave number, and stretching in general will occur at a higher wave number. I think with this animation, I will just stop this, and I will get on with my the routine presentation, what I'm doing. Okay, so this is the ordinary slide. This is the usual slide where I was going through, and here you have the different types. In a two-dimensional way, I have represented it: scissoring, you have rocking, you have wagging, you have twisting you have. And you see here that scissoring occurs at a higher wave number, because as I told you here, there is a problem with the two hydrogen atoms moving in the opposite direction. So among the different types of the bending vibrations, here you will have the highest wave number. And again, this is one concept, like it tells you how many bands you can have in the IR spectrum. In the IR spectrum, when you see LI as different from the NMR or the mass spectrum, what you have here is you get abundant number of IR absorption bands. Why you get that lot of bands in the IR spectrum? Why it's not like NMR, or why it's not like mass, where you have selected number of bands, where you have limited number of bands? The reason is there are plenty number of ways in which the different bonds within a molecule can vibrate. So how do you get the number of vibrations that are possible for a molecule? For every atom, if you can take, see, if I am, madam, can I alone annotate? No, it's not possible, no? I alone, can I annotate? Yeah, so I will just make use of one thing, and I will try to explain to you. Suppose if I am trying to make this. Suppose this is an atom. Okay, I'm trying to draw an atom. I'm not a good expert in it, but still I thought I can draw this atom. So here I have put a simple one atom I have drawn. All of you can see on the slide one green colored ball I have put over here. So if you take this particular green colored ball, perhaps it can move in three directions. One, it can move in x-axis. Another one, it can move along y-axis, and third, you can move along z-axis. So there are three ways in which this particular atom can be moving: along x-axis, along y-axis, along z-axis. So every individual atom, as we know, it will be having 3 degrees of freedom. 3 degrees of freedom. And what we assume is, when n number of atoms combines to form a molecule, the total number of degrees of freedom will be equal to 3n. The total number of degrees of freedom will be equal to 3n. Just a minute. I would like to clear off what I have drawn. Clear out drawings. Okay, it's gone. So what you can see here is, so previously, as we had seen, every atom, it will have 3 degrees of freedom. It can move along x, it can move along y, it can move along z. And what the practical thing is, when n number of atoms combine to form a molecule, since every atom is having 3 degrees of freedom, n number of atoms will be having totally 3n degrees of freedom. 3n degrees of freedom. And let us consider, for example, a non-linear molecule like water. Why you call it as a non-linear molecule? Because the three atoms are not in one straight line. They are in different. If you take this oxygen and hydrogen, this hydrogen is deviated from it. So you call it as a non-linear molecule. So if you take such a molecule like water, what you can see is it can move along the x-axis, it can move along the y-axis, it can move along the z-axis. So in all these three directions, you can see that the position of the molecule is changing. If you because ultimately, how do you designate the position of a molecule? You designate in terms of x, y, and z coordinates. So if I consider the position of the water molecule now, it will be having a particular x, y, z coordinate. Suppose if it is moving along the x-axis, from the cursor, if you can see, it is moving from this direction to this direction, along the x direction. What is happening? The x, y, z coordinate is changing. Similarly, when you move along y, when you move along z, in all the three possible ways, the position of this particular molecule is going to change. So you say that it has got three translational degrees of freedom. And next one is rotation. Let us think about rotating this molecule. I think all of you are able to see the pen which is on my hand. Okay, I'm
Yes,
trying
sir.
to rotate it along the x-axis. Okay, now this is a linear molecule, so don't consider this. Let me take a water molecule. Okay, I'm taking a water molecule. So in the center, you are going to have the oxygen and the two hydrogens. So when I'm rotating it in this direction, when I'm rotating in this direction, x-axis, the positions are going to change. When I'm rotating in the y direction, the positions are going to change. When I'm going to rotate it in the z direction, again the positions are going to change. So you say that there are three rotational degrees of freedom for the water molecule. So totally we have 3n, and we have isolated 3 for translation, 3 for rotation. As I already told you, the total is 3n. So what is the difference? 3n minus 6. So that comes out to be equal to 3. So you say that the water molecule can have 5 different vibrational degrees of freedom. And it is distributed as symmetrical stretching, asymmetrical stretching, and scissoring vibration. So this is the formula that you usually apply for finding the number of vibrational degrees of freedom that is possible for a non-linear molecule. It comes like this. But when you come to a linear molecule, see what is happening in the case of the carbon dioxide. If you can take a carbon dioxide molecule, what you can see here is if you take this particular carbon dioxide molecule, in the center where I have placed an index finger, let us assume it is carbon, and this side it is oxygen, this side also it is oxygen. Let us consider the rotational degrees of freedom. What will happen if it rotate in the x direction, x direction, x direction? X will remain at the same place. Carbon will remain at the same place. The two oxygen also will remain at the same place. So the rotation of this particular molecule in the x direction does not change the position of carbon or the oxygen. So you don't get any freedom around the x-axis. But when you rotate it along the y-axis, definitely the position changes. When you rotate it along the z-axis, definitely the position changes. So you say that it has got 2 rotational degrees of freedom. And translational degrees of freedom will remain 3. See, if you consider this carbon dioxide, it can move along x-axis, it can move along y-axis, it can move along z-axis. So how many number of degrees of freedom are left out? As I already told you, the number of degrees of freedom will always remain 3n. It is fixed. Minus 5, that is 3 plus 2. So remaining, it has got more number of rotational degrees of freedom. Here less. We had only, how much we had in the previous case? We had only 3, but here it is going to be 4. You are going to have more rotational degrees of freedom. Now, this is a theory of IR absorption. Already, I believe that the yesterday's speaker would have mentioned, but still, I would repeat the same thing for the people who are listening for the first time. So let us assume this particular bond. Let me assume it is a carbon, and this is chlorine, and you are having a carbon-chlorine bond. Obviously, the reason why I have put plus here, because carbon can always push the electrons more towards chlorine. So chlorine will be having a higher share of electrons. That's why it has got a negative charge. And carbon will be getting a plus charge. And what invariably happens, the distance between carbon and chlorine will keep on changing. It will decrease, it will increase, it will decrease, it will increase. And That is why you call it as a polar covalent bond. You call it as a polar covalent bond because the electrons are not perfectly shared between the two atoms. For example, if I'm taking a hydrogen here and a hydrogen here, the electrons will be perfectly shared. But now it is carbon and chlorine. The electrons are not perfectly shared. So you get a polar covalent bond over here. And you have one side plus and one side minus. So what happens when the distance between these two atoms will increase and decrease? There is always a dipole moment that is resulting. Am I right? We call it as a dipole moment because when two equal and opposite charges are separated by a distance, you call it as a dipole. So this is in fact a dipole. And the dipole moment goes on changing when these atoms are coming closer, moving away, coming closer and moving away. So this change in the charge distribution, there is a change in the charge distribution across this bond that produces an oscillating electrical field. So whenever, understand, a molecule is polar in nature, a polar molecule, why it becomes a polar molecule? It has got a polar bond. And when there is a polar bond, there is always a dipole. And when these two atoms are vibrating, that means the distance is decreasing and increasing, decreasing and increasing. Or inadversely, you say that when it is vibrating, what is going to happen? There is a change in the charge distribution. There is a change in the charge distribution across this bond. And obviously, it will produce an alternating electric field. It produces an oscillating electrical field. Again, I will just represent here something. What I'm trying to put here is a photon. I think all of you are able to see this. You are able to see here. I have represented again a green color photon. So these photons I represent which belongs to the IR radiation, infrared radiation photons. So this can also be vibrating. Top to bottom, it can be vibrating. In the upward direction, in the downward direction, it can be vibrating. So when these photons vibrate, again, this photon also will be producing an oscillating electrical field like this. So you are having two electrical fields being created. What are the two electrical fields being created? One, the electrical field which is created by the polar bond which is present in a molecule. And another one is the oscillating electrical field which is produced by the photon which is present in the infrared radiation. Now what happens when this frequency, that means frequency with which these two atoms are vibrating in the bond, when that frequency becomes equal to the frequency with which this photon is vibrating, there is a phase that is, or a resonance that is happening between the two electrical fields. That means whatever electrical field this IR radiation is going to produce and whatever electrical field this particular bond is going to produce, they will be in resonance with each other. And obviously what will happen? This particular bond, the carbon-chlorine bond, will absorb the energy of this IR radiation. And you say the IR absorption has taken place because these two fields are in resonance with each other. And obviously, when you have an IR absorption, you take this as a spectrum. The photon is not getting absorbed at a particular frequency. What is going to happen? The absorption is going to take place. And you are going to see this band over there. So this is what it, once again, I'll just repeat. Madam, am I audible, madam? Am I audible, madam? Okay.
Yeah,
so, yeah. Okay. So here you have the photons of the IR radiation. They are vibrating. They produce an oscillating electrical field. You have the bond which is vibrating. That is also producing an oscillating electrical field. Whenever the vibrations made by this photon and vibration made by this bond are equal to each other, they are in resonance with each other, what will happen? This energy will be absorbed by this bond, and you will have at that particular frequency absorption will take place. So any other photon of the IR with any other frequency, this particular bond cannot absorb. So these are the two basic requirements for the any molecule to absorb IR radiation. What are the two basic requirements? First thing, it should have a dipole moment. It should be a polar bond. And what is the second thing? This frequency, what is that? Natural frequency. You call it as natural frequency of vibration. This natural frequency of vibration should be equal to the frequency with which the photon of the IR radiation is going to vibrate. That time the resonance will happen and the molecule will absorb IR radiation, and you can see an IR absorption band. So all the molecules cannot absorb IR. The basic feature, it should have a dipole moment. So That's it. Now we are coming to the next portion of it here. So as we discussed before, here I'm having the carbon chlorine bond. As you can see here, it is the carbon chlorine bond over here. This is the ground state. So the carbon and chlorine are vibrating. What is the frequency with which they vibrate? Nu. Now I am having the IR radiation as I have drawn before. I have drawn here a photon. A photon is present over here. So that is also going to vibrate. And with what frequency it is going to vibrate? Nu. It is going to vibrate with the nu frequency. So what will happen? I hope my drawings are clear. I hope my drawing is clear. Okay. So now this photon is vibrating with nu frequency. The carbon chlorine bond is also going to vibrate with the nu frequency. As I said before, resonance will happen and this carbon chlorine bond will absorb this energy and it will jump from ground state to the first excited state. So it jumps and you get an IR absorption band, which I already mentioned to you that it is called as the fundamental band. So let us remember these terminologies. It is very important for us because otherwise no, we are tempted to use other types of terminologies like IR absorption band. Of course it is correct, but still it's a technical term. These things we can have, so it will be easier for us to put across to the people who will be able to understand. So this is called a fundamental band. Now, so the frequency of this photon matches the frequency of the vibration, and the molecule will be excited from ground state to first excited state, and the band that results, you call it as the fundamental band. In case if this particular photon is vibrating with twice the frequency, that means previously it was making only new vibrations per second, but now how many vibrations? Double. Now again what will happen, this carbon chlorine bond can absorb even that photon also, which vibrates with double the frequency, and thing is it will be excited from ground state not to the first excited state, it will be getting excited to the second excited state. It will not be vibrating, it will not be getting excited to first excited state, rather it will be getting excited to promoted to second excited state. And this band that results, you call it as an overtone. This you call it as an overtone. So this band represents an overtone. This represents a fundamental band. And what is the difference you can see? I have drawn here two IR absorption bands, right? One I have drawn that of a fundamental band and another I have drawn that of an overtone. From the slide itself, it is very clear what I have drawn here. It is a very, very weak band, overtone. So that is the characteristics of overtone. Overtones always will be very weak bands. In the usual IR spectrum, you cannot detect that overtone. In usual methods, you cannot detect the overtone. So it is always in multiples of these frequencies. Suppose if it is coming in suppose if the photon is vibrating with thrice the frequency, again it will absorb. But you cannot visualize that because sometimes it will fall outside the IR region. So this is so please understand these concepts, very important. One, you have the fundamental band, it corresponds to the natural frequency. Overtone band, it is twice the fundamental frequency. This is called as the first overtone. Okay, so I will move on to the next slide. Okay, so here I have drawn a carbon-hydrogen bond. Is it possible for me to predict, or if I am taking the IR spectrum of this carbon-hydrogen bond, is it possible for me to predict where this carbon-hydrogen bond will absorb, or what will be the natural frequency with which the carbon-hydrogen bond is going to vibrate? Or when you take an IR absorption spectrum, the frequency of the IR absorption radiation or the IR radiation corresponds to the natural frequency of this carbon-hydrogen bond. Am I right? Because whatever may be the natural frequency of this carbon-hydrogen bond, that frequency of the photon only is going to be absorbed from IR. So how can I calculate this? You can make use of the Hooke's law, where it tells that nu is equal to 1 by 2 pi z into root of F divided by mu. Mu means mass of this carbon into mass of this hydrogen divided by mass of carbon plus mass of hydrogen. Here I have put it mx into my divided by mx plus my. That is this mu. F represents what? The force constant. It has got something to do with strength of the bond. Again, I will just represent it here. Suppose if I am having carbon, single bond carbon, okay, the single bond is having a strength. On the other hand, if I am putting carbon and if I am putting double bond carbon, here you're having two bonds. So the strength of the bond will be more. Whereas if I'm putting C, triple bond C, if I'm putting three bonds, it's a triple bond. What will happen? The strength of the bond will be much more. So I'm just trying to give you an overall concept about the strength of the bond. It doesn't always depend upon single bond, double bond, and triple bond, but understand that between the two atoms, if I can have the bonds, always the triple bond will be having more strength, double bond will be having lesser strength, and single bond will be having the least strength. So the force constant has got something to do with the strength of the bond. So if I put this in the calculation, for carbon and hydrogen, if I can put the mass, I can theoretically work it out to be 9.3 into 10 raised to 13. That means if I take an isolated, I'm repeating that statement again, isolated carbon hydrogen. I'm not considering a carbon hydrogen bond within a molecule, like say methyl chloride or carbon tetrachloride. I'm not considering. I'm taking an isolated carbon hydrogen bond, and where exactly you will see that, if you take an isolated carbon hydrogen bond, how many times it will vibrate per second? 9.3 into 10 raised to 13. Just consider how many times. If you just put that 13 zeros, just imagine the magnitude of vibrations this carbon and hydrogen should be coming closer, moving away. So it is possible for us to predict it theoretically, how many vibrations it will be making per second. So it means that so what does this figure imply, or what is the importance of this particular figure? I have put it here in the slide. It means that suppose I am having a photon over here of the IR radiation, and if this particular photon is going to vibrate 9.3 into 10 raised to 13 times of vibrations per second. I will repeat. If this particular photon is going to make up and down vibrations, if it is going to vibrate 9.3 into 10 raised to 13 vibrations per second, then immediately this carbon hydrogen bond will absorb this, and it will be excited from the ground state to the first excited state. It will be going from the ground state to first excited state. It will jump from here to there. Okay, because it matches the natural frequency of the carbon hydrogen bond, matches the natural frequency of the, not the natural frequency, the frequency of the IR radiation. So that is a concept of it. Again, here I am coming back to that principle what we discussed. What is the importance of the dipole moment? If you take carbon dioxide, three types of stretchings can happen here. One is symmetrical stretching, asymmetrical stretching, bending. In the case of symmetrical stretching, what do you see? The two dipole moments are in the opposite direction because the two atoms are moving parallelly, not parallelly in phase. The two oxygens are coming towards carbon, moving away. So because of that, what happens? Whatever dipole moment, you know, it is a vector quantity. It always has a direction. So here, the direction of the dipole moment is from positive center to negative center. So from carbon to oxygen. Whatever dipole moment you have on the left hand side, the same dipole moment you are having on the right hand side also. So they will cancel, and resultant dipole moment will be equal to 0. And we already explained that the basic feature necessary for a particular bond to absorb the IR radiation is that it should have a dipole moment. Here we are seeing a particular case where the resultant dipole moment is 0. So in symmetrical stretching, the dipole moment is 0. So such a molecule, such a stretching vibration, when it undergoes, it cannot absorb the IR radiation. On the other hand, if you see this, it is an asymmetrical stretching. One side the bond length is increasing, another side the bond length is decreasing. So in effect, what happens? There is a a dipole moment for this molecule, and definitely it will absorb the IR radiation. Here you can see I have represented it in a two-dimensional way. What is happening over there? This is a symmetrical movement. This is an asymmetrical movement. One side it is increasing, another side it is decreasing. So that is what is going to happen. So only that is, this is one of the reasons. Already we said that number of degrees of freedom for a particular molecule is 3n, and number of vibrational degrees of freedom will be equal to either 3n minus 6 or 3n minus 5. So if you take a particular compound which is having say 5 different atoms, 3 into 5, 15, minus, if you cancel the number of translational degrees of freedom, and if you cancel the number of rotational degrees of freedom, lot of bands the molecule should be exhibiting, but it does not exhibit. Why? Because I told you this particular factor. Only those vibrations which are infrared active you can see in the spectrum. Other bands you will not be able to see that. And this is a repetition, like IR absorption bands, usually you notate it using wave number. You don't directly use the term frequency. Frequency, you don't express it. It is expressed in wave number. There is a simple conversion of frequency, because previously we said, no, in case of carbon-hydrogen bond, how many times it will vibrate? 3,100 times it will be vibrating, the carbon-hydrogen bond. How will you convert it into wave number? You just divide it by the velocity of the light and you will be getting wave number. So this is how you express it. So if you have this particular wave number, you take the either you take the reciprocal of the wavelength, or what you do, you take the frequency and you divide it by the wavelength, this one, the velocity of the light. The frequency you take, you divide it by the velocity of the light, and you will get wave number. So there are two methods of expressing the position at which IR absorption band will happen, either in terms of wave number or in terms of frequency. In all the cases, we will be expressing in terms of wave number only. And how wave number is related to frequency? Frequency you divide it by velocity of the light. So here comes the importance of coupled, that is Hooke's law we predicted. I hope all of you will remember, like in carbon-hydrogen bond, using the Hooke's law, we predicted that wave number should be 3,100 centimeter inverse. But if you see a methylene molecule, you will have the carbon connected to two hydrogens, not one hydrogen, two hydrogen. That is the reason why I said very specifically, I am considering an isolated carbon-hydrogen bond. But here, what carbon-hydrogen bond I am having is within a group, a methylene group. And there is a big difference between an isolated carbon-hydrogen bond and a carbon-hydrogen bond within a methylene group. It is not like this. What is the reason for that? In a methylene group, you have two hydrogens connected to a common carbon atom. So because of this, as we already discussed the stretching vibration, the distance between this carbon and hydrogen, when it is increasing, here also it can increase. That means both of them can happen, and in phase vibration, in phase stretching vibration can happen. What do you mean by in phase? Both the bond length will be increasing as well as decreasing in phase. That means when this carbon-hydrogen bond length is increasing, here also it will be increasing. When this carbon-hydrogen bond length is decreasing, here also it will be decreasing. That is what we call it as the symmetrical stretch. And here what do you have? In one case, when the bond length is increasing, another case the bond length will be decreasing. Or here when the bond length is increasing, here the bond length will be decreasing. This is not an in-phase stretching. It is an out-of-phase stretching. So you see here, one isolated carbon-hydrogen bond, when it is a part of a methylene group, it can exhibit two different types of stretching. What are the two different types of stretching? One is symmetrical stretching, another one is asymmetrical stretching. So if I can take the IR absorption band of a CH2 group containing compound, I'll repeat, if I can take the IR absorption spectrum of a CH2 group containing compound, by predicting or by using Hooke's law, I should get a single band at 3,100 centimeter inverse. At 3,100, I should be getting a single peak. But practically, what do you get? You don't get a single peak, but instead you will be getting two peaks. One corresponding to symmetrical stretching and another corresponding to asymmetrical stretching. That means one which is happening at 2926, another one happening at 2853. This is what we call it as the coupled vibration. It is very important for us as far as the interpretation of the organic compounds are considered. It is very important for us. So this vibration is called as coupled vibration. We will be coming across a couple of compounds where you will notice this coupled vibration, which is a very effective tool to identify the structure of the organic compound. For the time being, you understand there is a symmetric stretching, asymmetric stretching that can happen when two similar atoms are attached to a common carbon atom or a common atom. For example, if you are having nitrogen and two hydrogens, NH2, it can be symmetrical and asymmetric. NO2, nitro group, N double bond or single bond, you can have that. If you have a carbonyl group, C double bond and single bond, again you are going to have coupled vibrations. Then hydrogen bonding is another important tool. It is an important aspect in infrared spectroscopy. So what is hydrogen bonding? When hydrogen comes between two strongly electronegative atoms, one it will hold by a covalent bond, and another one it will hold by a weak electrostatic force of attraction, which you call it as the hydrogen bonding. So here I have taken the example of alcohol, ROH. Okay, if I'm taking this ROH, this hydrogen atom is in hydrogen bonding with another oxygen atom. So because of that, what will happen? The OH bond is going to get weakened over there. So there will be a weakening of this OH group. So you will be getting two peaks, one corresponding to the free OH group and another one will be corresponding to the hydrogen bonded OH group. Because obviously you know that the hydrogen is getting into a bond formation with the neighbor oxygen. It is a weak electrostatic force of attraction. So because of that, what will happen? This bond will get weakened, and that is why you are getting a broad peak over here. And you see the shift also. If you are getting an OH group alone, it will be showing an IR absorption band at 3600. You will be getting a sharp peak at 3600. But once it is contributing to a hydrogen bonding phenomenon, what happens? It is shifting to a lower wave number. So two things are happening over here. What is happening? What are the two things happening? One, the OH, which is hydrogen bonded, will show a peak at lower wave number. It reduces from 3600 to 3300. That is one aspect. Then another aspect is what? Instead of getting a sharp peak, you will be getting a broad peak over here. Two phenomena will happen. And the more the shift, more will be the strength of the hydrogen bonding. If you take this alcohol and carboxylic acid, by seeing the slide itself, it will be very clear to you. The strength of the hydrogen bonding is more in an acid. You can see that it is a dimer. Its strength of hydrogen bond is more because here you have a carbonyl group H. Between the same two molecules itself, you have two molecules. It's a dimer actually. But here what you take, this is one alcohol molecule, this is another alcohol molecule. So many alcohol molecules are having hydrogen bonding amongst them. But here what you can see, the same two molecules, between two molecules itself, you are having two hydrogen bonding. So the strength of the hydrogen bonding is more here. So in this case, what is going to happen there? The shift will be too much. The shift of the shift of the OH group that happens due to hydrogen bonding will be more in the case of an acid, because the strength of the hydrogen bond is more in case of an acid. That is what you see. Whereas in alcohol, you don't have that much strength of hydrogen bonding because so many molecules contribute towards the hydrogen bonding. Now, this I'm sure that yesterday also you would have listened and you would have heard this, you would have seen this particular slide. What is happening over here? You take here a pure liquid. So extensive, for example, the molecule what I'm going to take here is 1-butanol. So intermolecular hydrogen bonding is maximum over here. And that is why you are getting a broad peak at 3200 to 3600. Between that area you are getting. And in this particular case, you are just diluting it. When you are diluting it, what happens? The intermolecular hydrogen bonding is not happening much, because when you are putting more amount of solvent molecules, what is going to happen there? It will break these hydrogen bonds. So the hydrogen bonding strength is lost over here. That is the reason why you are getting a sharp peak. This sharp peak corresponds to the free OH groups. And here what do you see? You are taking a very dilute solution. You are adding a lot of solvent molecules. For example, 1-butanol, I'm taking in, for example, you take hexane. I'm adding a lot of hexane molecules. So all the 1-butanol molecules are separate. So there is no hydrogen bonding at all. So you are getting a sharp peak and is shifting to higher wave number. Whereas here, what is happening over there? It is a very dilute solution. So there is no hydrogen bonding. You are getting sharp peak. Here what I'm taking 100% pure compound. So the extent of hydrogen bonding is very high. So that is why the bond is shifted to lower wave numbers, and not only that, you are getting a broad peak. So see the left IR spectrum as well as you take the right IR spectrum. So both you will be able to see that. Now, here we are coming to the another aspect of it called the Fermi resonance. So what is Fermi resonance? Let me take the example of this aldehyde. Here we are taking acetaldehyde. So what about this carbon hydrogen? This carbon hydrogen bond, it can undergo stretching vibrations. This carbon hydrogen can undergo stretching vibrations, and already using the Hooke's law, we predicted that it should occur at 3100 centimeter inverse. So roughly we can say 2720 centimeter inverse. So this CH stretching will show an IR absorption band at 2720 centimeter inverse. But here the problem is this carbon hydrogen can undergo bending vibration also. And what will be the bending vibration? 1400. So here I'm telling two things. Carbon hydrogen stretching, it is coming at 2720. Then carbon hydrogen bending, how much is it coming? 1400. And already we discussed about the overtone. So what is an overtone? We already discussed. That means if you draw like this, the first will be an fundamental band. So this will be corresponding to a fundamental band. And second one will be an overtone. That means if the frequency is double this, it will get excited to second excited state. So that is what you call it as an overtone. So here what happens? The bending vibration is 1400. So what is the first overtone of this? It will be double this, 2800. So there is a matching. So the CH stretching will happen at 2720, and the first overtone of the CH bending will happen at 2800 because it is double this. So CH bending will happen at 1400. The fundamental vibrational band corresponding to CH bending is 1400. First overtone means what? Double this. So that is 2800. This 2800 is close to 2720. What is this 2720? CH stretching vibration. So there is a resonance between the two. That means there is a resonance between the CH stretching vibration and the first overtone of the CH bending vibration. So because of that, what is going to happen over here? I already said before that overtone will usually be a very feeble peak. Actually, this peak, what you are seeing, it is corresponding to the overtone, this peak. That is at 2820, you are able to see a peak. At 2820, you are able to see a peak. It is an overtone band. In usual circumstances, you should not be able to see this peak. But here, you are able to see this peak because this 2800 is close to 2720. So this overtone will absorb the energy from this band and you will be able to see it as a separate band. This is one of the prominent diagnostic band in case of an aldehyde. So in case of an aldehyde, you will be able to see a split peak. This is due to Fermi resonance. That is the resonance that is happening between the CH stretching of an aldehyde and the first overtone of the CH bending. This is what we call it as Fermi resonance. So this is a diagnostic band for the identification of an aldehyde. So what are the requirements to be fulfilled when we are trying to interpret a particular spectrum? What are the different requirements to be fulfilled before interpreting a particular spectrum? First of all, the particular spectrum should be adequately resolved, and the spectrum should have maximum intensity also. The intensity is also very, very important. The compound should have reasonable purity. The spectrometer should be properly calibrated, and method of the sample handling, it should be specified, because that is very, very important. So all these four things you can take care of it, then you can be sure that you will be able to get a very good compound, very good spectrum for the compound. So these are the things which is very important. So what are the four things that is very important? First of all, adequate resolution of the peak should be there. The peak should be properly resolved. Otherwise, what will happen? I will just put over here. Suppose you are having two peaks. See this difference? You get two peaks like this. You are able to make out between the two peaks. On the other hand, if you are getting a peak like this, these two peaks is obscured. Am I right? So resolution is very, very important. It should not look like this. It should look like this. Intensity of the spectrum is very important. I previously said that in case of an overtone, you get small peak like this. You cannot distinguish it. Whereas Intensity, if is very high, only you will be able to identify. So you should select those bands where the intensity is reasonably well. Then purity of the compound is very important. Sometimes what will happen, your compound will be mixed with the water, and again it contains an OH group, and that can give a peak, and you will misinterpret for an OH group in your compound. Spectrometer should be properly calibrated. It's very important. For example, you are supposed to get a C double bond O group at say 1750. This is the actual value. Let's assume it's an actual value, but you have not calibrated the instrument properly. So because of that, what is happening? You are getting the peak at say 2000 or so 2000. You are supposed to get a peak actually at 1715, but the instrument is not proper. It's not properly calibrated. So you are getting a 2000. So you will feel that your compound does not have a C double bond O group. So the instrument should be properly calibrated. That is very, very important. Method of sample handling has to be specified. Again, this I will take you to the hydrogen bonding slide. See here. Here you are using a pure liquid. That is why you are getting a broad band. But on the other hand, in this case, what is happening? You are not using a pure liquid. You are not using the pure sample. You are mixing this 1-butanol with solvents. That is why you are getting a sharp peak. So definitely the method of sample handling should be specified, because in the presence of a solvent, it will be showing like this peak, like this wave number. Whereas in the absence of a particular solvent, it will be showing different. Here you can see that 1-butanol in the presence of a hexane as the solvent, you will be getting this peak. Whereas the same 1-butanol, when it is highly concentrated, in the absence of a solvent, you will be getting another peak. So this is very, very important. The sample handling has to be mentioned. These base values, please make sure that you remember these base values. OH, NH, CH, C triple bond N, C triple bond C, C double bond O, C double bond C, C single bond O. These values are very, very important. Understanding these values will help us to predict what will be the value corresponding to OH group when it is a part of carboxylic acid. For example, if I know that see, what is the value I am remembering? I am memorizing it as 3600. This can be a part of C double bond O OH group. That time, the value of this OH group will be around 2500 to 3300, around something like that. Okay, 2500 to 3300. Similarly, if you take the same OH group of an alcohol, it will be around 3650. So if I know this OH value, I can definitely understand that the OH group which is present inside a carboxylic acid or an alcohol will be around this 3600. So later on, it will help you in remembering these values. Similarly, NH, it can be a part of an amine, it can be a part of an amide. Similarly, C triple bond N, it can be a part of an aromatic C triple bond N, aliphatic C triple bond N. So depending upon the environment around this OH group or NH group or CH, this value will change. But that value, I can easily remember it provided I know these base values. So please make a note of these base values: OH, NH, CH, C triple bond N, C triple bond C, C double bond O, C double bond C, and C single bond O, C single bond O. So here, whenever I get an IR spectrum, which are the two portions in the IR spectrum that I should be looking in for? First of all, it is a region between 1300 to 4000 centimeter inwards. That is, this region is 1300, this is 4000. This region what you should be looking in for first. You can see here that comparatively very less number of bands you will be getting in this portion of the spectrum. You will be getting very less number of bands in this portion of the spectrum. And almost all the functional groups like OH, NH, C double bond O, etc. will be occurring in this region of the spectrum. So you can detect the main functional groups by looking into between this 1300 to 4000 centimeter inverse. The next region that you should be looking into is the region between 650 to 900 centimeter in 650 to 900 centimeter inverse, this region of the spectrum. All the bending vibrations will be occurring in this portion of the spectrum. All the bending vibrations will be occurring in this particular portion of the spectrum. So two regions are very important. One is the region between 1300 to 4000 centimeter inverse. It represents all the stretching vibrations. And another one is the region between 650 to 900 centimeter inverse that represents the bending vibrations. You get a region between 900 to 1300 centimeter inverse. You get a region between 900 to 1300. What is the significance of this region? Here I've taken two molecules. One is mono-substituted, another one is di-substituted. If I take the mono-substituted and di-substituted, you can see that the functional group region, if I can take, that portion is looking the same here. So here you can see that this particular region, the region between this 1300 to 4000 region, in both the cases, it is nearly the same spectrums you are getting. But if you see the region between 650 to 900 centimeter inverse, in both the cases, it is really different. So this fingerprint region is unique for every molecular species. You take any molecules, even a small change in the structure of the molecule also, it will be reflected in this region of the spectrum because it represents the skeletal vibrations of the molecule. So here I'm repeating once again, you are taking a di-substituted alkane, you are taking a mono-substituted alkane. The region between 1300 to 4000 centimeter inverse in both the spectrums will be looking same. But here, if you see, carefully analyze this short region between 650 to 900, in both the cases, you will see a typically different spectrum because this region represents the skeletal vibration of the molecule as a whole. And this is how this particular region can be used for distinguishing between the structures. That means you have these two compounds and you want to know whether both the spectrums are same, both the compounds are same. Somebody is giving you two compounds, say a compound A and compound B, and they are telling you that you please identify whether these two compounds are one and the same. What you should do, you should take spectrum of the first compound A, you should take the spectrum of the second compound A. And when you preliminary you do the analysis of the spectrum, what you can observe is the beginning portion of the spectrum. That means the region between 1300 to 4000 will look the same. And you will come to a confirmation that both the molecules are the same. But if you again consciously analyze the fingerprint region of the spectrum, that means if you check between the region of 900 to 1300, you can see that there is a difference between the two spectrums. So there you can identify that both the compounds A and B are not one and the same, they are different. So that is how you identify them. So this is the significance of fingerprint region. So you cannot elucidate the structure of a molecule from this, only you can differentiate or distinguish between whether the compounds are same or not by making use of the fingerprint region. And now we are going to get into this process of interpretation of the IR spectrum. And this group is the most important group, the C double bond O group. The reason why we go for a C double bond O group, because this particular group will always show in the spectrum. This particular group will always show in the spectrum. Why? The C double bond O group always you can see in the spectrum, because it is the group which is having the strongest dipole moment, and its Bayes value will be around 1715 centimeter inverse. and it shows the lowest value of 1640 and highest value of 1830. So I'll repeat once again. Whenever you get the IR spectrum in the hand, the first IR absorption band that you should be looking in for should be the C double bond O group. The reason why you should be looking for a C double bond O group is if your molecule contains a C double bond O group, definitely it will be visible in the IR spectrum, because the C double bond O group is going to have the highest dipole moment. So you can see that in the spectrum. So the next one. So here I'm having the butanol. It is a ketone molecule. So already we explained the base value of C double bond O. What is the base value of C double bond O? We remember that it is 1715 centimeter inverse. We remember the base value of, see here, the base value of C double bond O, 1715 centimeter inverse. I'm going back to my slide again. See here, I've got a ketone. And what about the base value, 1715? See the characteristic nature of this particular peak. It is the strongest peak, the most intense peak you can see in the spectrum. You can never miss this band. And not only that, if you take the left and the right portion of the spectrum, it occurs right in the middle of the spectrum. So you cannot neglect or you cannot miss out this band. So first go for checking whether your compound contains a C double bond O group or not. Next one. As you see here, on my left hand side you have the anhydride, and on my right hand side you have the amide. And see the range of C double bond or stretching vibrations when you go from left to right. In the case of anhydride, you are having the highest wave number. And in case of an amide, you are having the lowest frequency. That means in case of amide, you have the C double bond O, which is exhibiting the lowest frequency. And in case of anhydride, you have the C double bond O exhibiting the highest frequency. That means the strongest C double bond O you get over here. The weakest C double bond O you get over here. Why I am telling it is strongest and weakest? I hope you remember. Using Hooke's law, you can predict the frequency of a particular bond. What is Hooke's law? Nu is equal to 1 by 2 pi C into root of F by mu. F represents what? The strength of the bond. So when the strength of the bond increases, obviously the frequency also will be more. So in this case, if I am getting the C double bond O appearing at a lower frequency, ultimately it means that strength of the C double bond O is less. Here if I am getting the C double bond O at a higher frequency, it means that the strength of the C double bond O is more. You see this bond length also. As I told in the previous slide, here you are getting the lowest bond length, which means the strongest bond. The electrons are perfectly shared between carbon and oxygen. That is why you are getting the strongest bond, you are getting the lowest bond length, and you are getting the highest frequency. And as I said in the case of amides, you are getting a very weak bond. See the bond distance, bond length distance, 1.248. Weak bond. You are getting it at a low frequency, 1680. So remember this carbonyl stretching vibrational frequencies when you go from one function group to another function group. Why this happens? Very important for us. Usually people dislike this infrared spectroscopy because they need to by heart a lot of values. But I would like to state that if you understand the reason why the C double bond O group or any group will exhibit a particular frequency of vibration, then it is easy to remember it. It will make the task a little more interesting rather than simply trying to mug up or by hearting the values. What could be the reasons? Whenever you have a particular group which can donate the electrons to carbon atom, already we learned that carbon is compared with oxygen an electropositive element. It will try to donate the electrons to oxygen. So the bond will be polarized. So carbon will be having partial plus, and oxygen will be having partial negative charge. That is why you say it is having a dipole moment. It will absorb IR radiation. Now, with the presence of alkyl group, what happens? The alkyl group is trying to donate the electrons to carbon atom. So in that effect, the bond is getting weakened. And what will happen? Once the bond is getting weakened, the frequency will be shifted to lower wave numbers. That is the reason why whenever you have an group which can exert a plus inductive effect, it will weaken the C double bond O, and the C double bond O stretching vibrational frequency will always occur at a lower wave number. Similarly, on the other side, when you have a group which can withdraw the electrons, what will happen? The polarity will get reduced. Why the polarity will get reduced? Because previously I said the carbon can be partially positive, oxygen can be partially negative. But here what happens? The carbon cannot effectively donate the electrons to oxygen. Why the carbon cannot donate effectively, can share the electrons with oxygen? Because here the electronegative element tells carbon, don't do that because I need the electrons. So what happens? The bond is getting strengthened over here, and this carbonyl stretching frequency will be shifted to higher wave numbers. It raises its absorption frequency. Two factors: electron donating will reduce, electron withdrawing will enhance, or it will shift it to a higher frequency. What happens here? We studied plus mesomeric effect. That means those atoms which are having lone pair of electrons, like nitrogen, it is having lone pair of electrons. Those electrons can be contributed into this bond. So obviously what will happen? The carbon will try to give those electrons to oxygen. So in that effect, what will happen? The bond will get weakened over here. The carbonyl bond oxygen, the carbon oxygen bond strength will come down. It will weaken the bond. So when the bond is weakened, the strength of the bond is decreased. When the force constant is coming down, obviously we know that the stretching frequency will come down. It lowers its absorption frequency. Similarly, hydrogen bonding, already we learned. It doesn't affect the OH bond alone. We already learned that the OH stretching vibrational frequency will be shifted to lower wave number. We already said in the case of hydrogen bonding. Similar effect will happen with C double bond O also. The C double bond O bond also will get weakened. It will be shifted to lower wave numbers. So these four effects, it should be there at your fingertips. It will help us in understanding the concept very easily. What are those factors? Electron donating group will shift it to lower wave number. Electron withdrawing group will shift it to higher wave number. Those atoms which are having lone pair of electrons, again, it will be shifted to lower wave numbers because it will weaken it. Hydrogen bonding will weaken it. So here again an example, double bond, it weakens it. See here the C double bond O, you are expecting it at 1715, but is shifting to 1690. So now I have put here the sum total of all that we had seen now. What is that we had seen now? Towards the left, as you can see, the stretching vibrational frequency goes on increasing. Why? Here you have all electronegative elements, oxygen, chlorine, oxygen, all of them try to attract the electrons towards itself. So because of that, the bond is getting strengthened, and you will have the C double bond or stretching vibration occurring at higher wave numbers. And what is this A factor? In case of ketone, I already mentioned, the R group and alkyl group will donate the electrons. When it donates the electrons, weakens it. So the frequency will be shifted to lower wave number when compared with that of an aldehyde. Acid, nothing to say further. Exclusive hydrogen bonding, it weakens it, 1710. In case of an amide, of course, nitrogen is an electronegative element. It can withdraw the electrons. But the other part, it is having lone pair of electrons, because of which it can donate the electron. So two factors with respect to nitrogen. Nitrogen can behave in two ways. Nitrogen is an electronegative element. It will withdraw the electrons. It will pull the electrons from carbon. Another effect is plus mesomeric effect. Nitrogen, it is having lone pair of electrons. These electrons can be given to carbon, or plus resonance effect, plus mesomeric effect. Because of that, what will happen? The carbonyl stretching vibrational frequency will be reduced, because the C double bond O bond strength will be reduced. That is why you are having the lowest wave number over here, 1690. This is very important slide, because all the carbonyl stretching vibrational frequencies, how comparatively it varies, I have displayed in the slide over here. And majority of the organic compounds that we come across, it will have a C double bond O functionality in it. This slide I'm not going, because later on we'll be seeing it. Now I will directly go for this alkyl groups now. Madam, am I audible, madam?
Yes, sir. Yes, sir.
Okay.
Sir, please proceed, sir.
Yeah, okay. this portion.
Yes, sir.
This is very, very important portion. Like you have ultimately the skeleton of the molecule. It can be either a double bond, or it can be an aromatic compound, or it can be an aliphatic compound. So we need to know how it varies. We check the hydrocarbon portion. So this already we discussed. For example, we have a methyl group, and the type of the factor that affects here is coupled interaction, because the 3 carbon hydrogen, previously we discussed about methylene group where we had only 2 hydrogen atoms, whereas in the case of the methyl group we'll be having 3 hydrogen atoms. So what can happen here? All the 3 hydrogen atoms are moving away, coming back, moving away, coming back in the same phase. You call it a symmetrical stretching. And another one where it is not in phase. Some are moving towards, some are at the same time, another one is moving away. So it can happen in asymmetric stretching. And always keep in mind, the asymmetric stretching, irrespective of the type of the group, will always occur at a higher wave number. Whether it is amino group, whether it is C double bond O group, any group you consider, asymmetric stretching will always have the frequency or the fundamental band will be occurring at a higher wave number when compared with that of a symmetrical stretch. So here also, asymmetrical stretch is 2962, symmetrical stretch is 2872. It is lesser than this. Next group, what we come across, this is a usual group that we will usually come in most of the organic compounds. That is the reason why I have put this first slide. Next one, what we come across is the methylene group, CH2 group. Again, you will have symmetric and asymmetric. Already we discussed in length. Asymmetric will occur at higher wave number 2926, and symmetric will come at lower wave number of 2853. So these groups, you please make a note of it. Similarly, we talked about the stretching vibrations. What about the bending vibrations? Because the bending vibrations are also diagnostic bands. So if we have a methylene group, CH2 group, we already learned, no? Wagging, twisting, rocking, scissoring vibrations and all that. Those are all of the bending vibrations. So if you have a methylene group, the symmetrical bending vibration will occur at 1465. Please make a note of it. Methyl group, if it undergoes a symmetric, if there is only one methyl group in a compound, if one methyl group is there attached to a carbon atom, you will get a single bending vibration at 1375. One peak you will get. If you are having 2 methyl groups, I mean an isopropyl group, this band will be split into 2 bands. You will get it one, you just remember it easily. You add 5 to this, it becomes 1380. You subtract 5 from this, it becomes 1370. You will get 2 peaks. If you get only 1 methyl group, you will get 1 peak. If you have 2 methyl groups, you will be getting 2 peaks. Suppose you have 3 methyl groups, I mean a tertiary butyl group, how it will be? You will be again getting 2 bands, only thing you have to add 10 to this, 1390. I think all of you can remember very easily these values. 1465, 1375, add 5 to this, 70, subtract 5 from this, 1380. Again, keep the same thing on the right, 1370 constant, and you reduce it, it becomes 1390. In both the cases, you will be getting 2 peaks. One is isopropyl, one is tertiary butyl group. So here, I will just show the spectrum. What do you see in the spectrum? It got a lot of methyl groups, methylene groups. So what about methyl group? It can give symmetrical stretching, then asymmetrical stretching. That is what you are getting here. CH. Symmetrical and asymmetric. 2872, 2962. CH2, symmetrical and asymmetric, 2853, 2926. What does these represent? The bending vibration. How many bending vibrations will you have in this molecule? Methyl group will show a bending vibration. We have already learned 1375. See here, it is coming around 1381. Similarly, the methylene group, it will show a bending vibration at 1462. We predicted it at 1465. Don't go for the exact values, because previously when I said 1375, never expect that all the methylene groups will be showing at 1300, and methyl group will show bending at 1375 itself. Little bit variation can be there. There can be plus and minus 10. Okay, plus and minus 10 or 20, near about it can be there. Don't go for the exact values, but typically it tells you. See here, the symmetrical CH2, the symmetrical CS3, you get 2 bands. Take this particular compound. Again, it's an isopropyl group what you are having. It is an isopentane molecule. Here, You are having here an isopropyl group. As you can see over here, it is an isopropyl group. CS3 connected to CH1 CS3. So what is happening over there? You will get a split here. Already we had split it. 1375, you reduce 5, 1370, you add 5, it becomes 1380. Previously we had seen. Hope you remember this particular slide. See here, 2 peaks. You will get 2 peaks for isopropyl. Those peaks only you are getting there. This peak, 2 peaks you are getting. Then methyl group, definitely it will show CH stretching vibrations. You can see over here. The CH3 and CH2 will peaks over here. 2962, 2926, 2872, 2853, all these CH stretching vibrations you will get. It is a very clean spectrum. No much of bands you can see here. And see the stretching 1300 to 4000. We already mentioned that is a group frequency region, functional group region. It is comparatively very clean here. Why? Because you are having only CH2, CH3 and CH groups over here. On the other hand, if it is an aromatic or alkenic, you would have got a lot of vibrational bands over here. Now, so we have discussed now the aliphatic portion of the molecule. Now, I will try to discuss the double bonds. So I'm just changing the order of the slide so that it will help us later. Okay. So the next common functionality which you will see in most of the organic compounds is double bonds or aromatic rings you will see in the compound. So CH3 and CH2 or CH is integral part of most of the organic compounds. Without that, you don't have the organic compound. Next, what we come across is the presence of this double bonds or aromatic rings. So if you have a C double bond C, if it is an alkene, you will get a peak between 1640 to 1667. Whatever I'm putting in the slide, who are interested can make a note of it because it will help you. Finally, when I'm going to give the problems, it will help you out. That's why I'm taking sufficient time when I'm trying to display the slides to you. You can make a note of it. Sir, I am audible, no sir? I'm audible?
Yes, sir. Yes, sir. Yes, sir. Please proceed, sir.
Okay, sir. Okay. 1640 to 1667. You will get a peak at this particular place due to the C double bond C. If you get a benzene ring, you will be getting 2 peaks. One between 1585 to 1600 and another between 1400 to 1500. So what is the difference between an alkene and an aromatic ring? In case of an alkene, you will get, remember the base values, what we learned before? Can we just go back once to the base values? Just few seconds. See these base values, have a look. C double bond C, it should give around 1650. So keep this in mind when you are discussing alkene or when you are discussing about aromatic compounds. First thing what you should have in mind is 1650, C double bond C. Then we will go to that slide. Okay, we come to the slide. So you see 1650 lies between the two. And what is the maximum value it can have? The C double bond C, 1667. What is the minimum value that you can have? It is at 1640. You can see that. In case of benzene, again, you will get 2 types of bands. What are the 2 types of bands you will get? One you will get between 1585 to 1600 and another one between 1400 to 1500. And conjugation lowers the value. Already we learned plus mesomer effect, plus resonance effect, presence of C double bond C next to it. For example, you are having not one C double bond C, you are having a conjugated diene or conjugated triene or conjugated tetraene. So many C double bond C, alternate double bond, single bond, double bond, single bond. What will happen? The C double bond C will be shifted to lower frequencies. That's what. Here you see. It's a very important slide. It gives you a fair picture of different types of alkenes. See here. If it is monosubstituted, this is the first example I had put before you. I think we were discussing about alkene. I told you that 2 different type of alkenes will be there and what is the importance of higher absorption spectra and all. So you will be getting two strong bands. You cannot miss out these bands. It's a typical characteristic pattern for any mono substitute alkene. That is a vinyl alkene. Where you will get this? 905 to 9. You please make a note of my audio. 905 to 950, 985 to 995. You will get two peaks. 905 to 915 and 985 to 995. You will get two peaks. Strong peaks you will get. And down also you can see this band. Between 900 to 1000, you can see these peaks. This peak you can never miss. If it is di-substituted, again there can be two types. One is the cis form, another one is trans form. You will surely agree with me that in case of the trans form, the bond is quite strong over there. Am I right? Because it becomes symmetry. The molecule becomes symmetric. So the dipole moment will be there. So because of that, the bond becomes stronger. The dipole moment is there, but it will be much more stronger. The bond will be much more stronger because of the symmetry there. So because of that, what you can see over here, in case of a trans, you will be getting it between 960 to 980. Can you differentiate between a cis and trans by this? Cis and trans, can you differentiate? The same isomer, geometrical isomer, when it comes to cis, it will be shifted to lower wave number. And what is the value? 665 to 730. Because why? The bond here is comparatively weak. Why the bond is comparatively weak? Because the bulky groups are coming on one side. Whereas here, the bulky groups are on the opposite side. The bond is little more stronger over here. Here, the bond is not that strong. You can easily vibrate the molecule. That is why you're getting it between 665 to 730. Whereas here, you are getting it between 960 to 980 centimeter inverse. This is vinylidene. You are getting two alkyl groups substituted to the same carbon atom, vinylidene molecule. You can easily remember it. Here, vinyl, what is the value? 905 to 950, 985 to 995. Am I right? You subtract 100 from 985 to 995. It will become 895 to 885. That value only you will be getting here. Suppose if it is vinylidene, you can see that it becomes 800 to 900. That is 885 to 895. You should apply some tricks also to remember these values. As I told you here, it is 985 to 995. You subtract 100 from this, 885 to 895. You will get for vinylidene. Cis and trans, you can easily remember this. Because trans is comparatively stronger bond, cis is comparatively weaker bond. Weaker bond means what? You will get it at low wave numbers, between 665 to 730. This will occur at 960 to 980 because it's a strong bond. These are all I am telling about the carbon-hydrogen bending vibrations, out of plane bending vibrations. Already we mentioned OOP, CH out of plane bending vibrations I am telling. Again, these are very important diagnostic bands. Similarly, I have displayed here tri-substituted also 790 to 890. It's a medium band that you're getting. So have this particular slide and the values, you can make a note of it and it will help you in the interpretation process. So let us come back to this. We are trying to interpret this compound. Alkenes. What did I say? Let us take the knowledge that we have gained before. We tried to compare between an aliphatic and alkene, no? Let us apply that knowledge over here. If it is an aliphatic, what will happen? You will get it below 3000. I hope all of you remember 2962, 2872, 2853, 2926. All this comes below 3000. It represents the aliphatic portion. Alkene, CH stretching vibration. Already we mentioned CH stretching vibration, it will come above 3000. Above 3000. You remember the base values? What was the base value for an OH? 3000. In case of an alkene, it will be coming above 3000. This, please have this in mind, very important information. This particular peak will be one of the very, very important and the only diagnostic band to differentiate between an aliphatic and an alkenic or aromatic portion of the molecule. This bands, what you get below 3000 always represent the aliphatic portion. It can be an alicyclic, it can be an aliphatic. But here it represents the alkenic portion. C double bond C, whether it is coming in a benzene ring or in an alkene ring, it will come above 3000. This value will be between 3000 to 3000 78 centimeter inverse. Please make a note of this. Very, very important. Later on, it will help you in the interpretation pattern. And what type of bands you get here? See, it is a mono substituted. Already we said, if it is a mono substituted vinyl group, you will get two peaks, 905 to 915, 985 to 995. You get the peaks here. Characteristic peak. This is CH, out of plane bending vibration. You are getting two peaks over here. You see the peak that you get. See here, two peaks. C double bond C, already we mentioned. 1650, I think all of you will remember the base values that we mentioned. Let us come to the next one. Again, it is a mono substituted alkene. Can we interpret all that we have learned now? C double bond C, alkene. Am I right? 1640 to 1667, you are getting it. Then similarly, CH of an alkene, it will show above 3000. Above 3000. You are getting this peak above 3000. But in this case, you are getting even below 3000 also. Why you are getting below 3000? Because there are CS3, CS, saturated alkyl groups are also there. That is why you are even below 3000 also you are getting a band. So this portion, if you take, it clearly tells you that the molecule has got both saturated and unsaturated. One thing. And not only that, it contains saturated and unsaturated, it contains an alkene. And what is the type of the substitution? Mono substituted. So you will get two peaks, 905 to 915, 985 to 995. You'll get peaks here. C double bond C, single peak between 1640 to 1667. Now, another important aspect. So we discussed about aliphatic portion of the ring molecule. We discussed about the alkenic portion of the molecule. Now the most important, the aromatic portion of the molecule, benzene. You cannot have a molecule without benzene ring. Very rarely you come across organic compounds. So this is also important. The aliphatic, the alkenic, and the aromatic. So here, I'm talking about the low frequency region between 650 to 1000 centimeter inverse, how those bands will help you in identifying the compound. So here you have mono substituted. So here, what and all do you have? Carbon, hydrogen, carbon, hydrogen, carbon, hydrogen. So they will give out of plane bending vibrations. Mono substituted, like a photograph you can see here, two strong bands, one around 700 and another around 750. Please make a note of this. 700 and 750. If it is mono substituted, CH out of plane bending vibration, two peaks you will get close to each other. A split peak you will get. Where one at 700, another one at 750 you will get. Now, next one, ortho disubstituted. Two people. Am I right? They are very good friends. So they don't split. They will give you a single peak. Around where it comes, at 750 it comes. You will get a single peak, 750. So if you have a ortho disubstituted benzene ring, directly look into the CH bending vibration, you will get a single peak, a sharp, strong peak at 750. If it is meta, you will get three peaks, 700, 800, 900. Very easy to remember, 789. 700, 800, 900. Para, always a villain, always a problem. You will get a strong peak around 800. Single peak, strong peak like 800. So these values you can easily remember it. Mono substituted two peaks, 700 and 750. Disubstituted single peak at 750. Meta three peaks, 700, 800, 900. Para always gives a single peak at 800. The other things you can just have it to have these informations like 124, 123, 135. Also these informations you can note it from the slide if you want. Now, here is the region between 1667 to 2000. That's what I always say. In infrared spectroscopy, the spectrum, every region can be important to us. Here, see the pattern that we are getting between 1667 to 2000 centimeter inverse. 1667 to 2. See the pattern of the peaks that you are getting. See the comparative intensity of each peak. And that will give you information regarding the type of the substitution. I will demonstrate it with an experiment for you, an example for you. Here you have toluene. It is mono substituted. Let us put up all what we have learned. What did we learn? What did we learn? Alkyl group, CH3, no? It will show peaks below 3000. Of course, 2925. Aromatic CH will be showing stretching above 3000. Already we learned above 3000. See, you are getting 3000 to 3100. You are getting the peak. See, two peaks. It clearly tells the compound contains both aliphatic as well as aromatic portion. Now, it is mono-substituted. So, a mono-substituted benzene ring will give you two peaks between 700 and 750. Can you see that? 700, 696. 750, it is 731. You are getting two peaks. What about these peaks? What does it represent? Whenever you have an aromatic ring, the C double bond C will show two peaks. Already we learned. C double bond C. See here. C double bond C of the benzene ring. It will show two peaks between 1585 to 1600 and 1400 to 1500. That is what you are seeing here. See here. 1400 to 1500, 1585 to 1600. We are getting two peaks for a benzene ring. And multiple other peaks you are getting. Because of the methyl group, you will get CH bending vibration and all. See here. I just noted it, that's all. See the pattern of the band that you're getting between 1667 to 2000. This is what I'm telling you. You compare with this particular chart, it resembles the first one, so it is mono-substituted. Again, we are coming to the next compound. It is orthoxylene. What happens in case of orthoxylene? I just want to drag some windows are there before me. So what do you see in the case of the ortho-substituted? If you take an ortho-substituted, I told you will get a single peak at 750. You are getting here a single peak at 750 centimeter inverse. You are getting a single peak at 750. That is a CH out of plane bending vibration, a single peak at 750 you are getting. Then what are the other things? Aromatic CH. It is giving above 3000. Can you see this portion of the spectra? Above. See the pattern of the band that you are getting here. In case of ortho substituted, see the pattern 1667 to 2000. Same thing is getting repeated over here. C double bond C. In case if it is aromatic, you will get two peaks. 1585 to 1600, 1400 to 1500. You are getting two peaks over here. Paraxylene. You are getting here aromatic CH above 3000. Again, you are having two methyl groups over here. So you are going to get above CH, above 3000. Below CH also you will be getting. Below CH, below 3000. This corresponds to the methyl groups. Then see the pattern of the band that you are getting. In case of para, see the para band. In this chart, I have put a particular pattern of the band. You get between 1667 to 2000 centimeter inverse. You get the same pattern over here. And it is para. So you will get a single peak at 750. So all the peaks tells you about the fact that the compound contains both aliphatic and aromatic portion. It is a disubstituted. It is a para disubstituted. All these informations you are getting. Meta. Three bands you are getting, 700, 800 and 900. You are getting three peaks. See the pattern of the metaxylene. Here I put meta. See this pattern, metaxylene here and here, 1667, 2000. Yes. Both aliphatic CH and aromatic CH you can see. C double bond C. Again, two bands you are getting. Then check for the triple bonds in your compound. The triple bonds will occur between 2240 to 2260 and C triple bond C will occur between 2100 to 2260. Again, these bands you can definitely see, C triple bond and bands you can definitely see because it has got a very big dipole moment. So mark this, please make a note of it. C triple bond N and C triple bond C. C triple bond N, it will come around 2250, 2250. Average value will be 2250. I think already the base values you remember, 2250. C triple bond C, 2150. So those values you can remember it. Here you have the alkynes. Can you see here? CH stretch of an alkyne. CH stretch of an alkyne. It will be the highest. It will come around 3267 to 3333. See, 3267 to 3333 it will come. C triple bond C, around 2250 will be getting it. CH bending 610 to, so these are the three diagnostic bands to find out an alkyne. What are the three diagnostic bands? CH 3267 to 3333, then around 2250 you will be getting a band, then CH bend you will be getting between 610 to 700. Keep this in mind. Same pattern. CH, always these double bonds, triple bonds will come after 3000. Above 3000, you can see alkene, alkyne, all of them will show above. Aromatic, but in the case of alkane, it will be highest CH 3267 to 3333, and C triple bond C, this much. Nitriles, C triple bond N, you see here, you are getting a sharp band over here. What about here? You are not getting any band above 3000. Why you are not getting any band above 3000? Because the compound does not have any alkenic double bond or aromatic double bond is not there. That is why you're not getting any peaks above 3000. Only below 3000 you have, because you are having only CH3, CH2 and all. See C triple bond and see the sharpness of the band, intensity of the band is very much strong. Why? Because this is having strong dipole moment. Another C triple bond, dipole moment and all that things. Nitro groups. So what about nitro groups? Already nitrogen is connected to 2 oxygen. So you are definitely going to have coupled vibration. So when you have coupled vibration, already we discussed, you will have a symmetrical stretching as well as asymmetrical stretching. That is why you are having here 2 bands. One here, 1300 to 1390, and another one will be between 1400 to 1500 you will be getting. 2 peaks you will be getting. 1500 to 1600 you will be getting, and another one between 1300 to 1390. 2 peaks you will get. If the compound contains a nitro group, symmetric and asymmetric stretching will be there. So hydrocarbon portion already we finished. Then we discussed about the nitro groups. We discussed about the nitriles. We discussed about the alkynes. We discussed about the triple bonds. We discussed about the different aromatic rings. We discussed about the alkenes. And now we will be moving on to the C double bond O groups. So here we start with. So if the molecule is an acid, what and all we can see? Already explained to you. What is the base value? 1715. But what is the value for an acid? 1710. It is less when compared with that of an base value. Why? Extensive hydrogen bonding. This is the pattern you get. And an acid will always contain an OH group. See the pattern of the OH group that you are getting. You are getting a broad band. And where you are getting between 2500 to 3300. Here you will see that the OH stretching is shifted to very low wave number. This will be the lowest wave number you can observe for an OH. In case of an acid, you will see the lowest wave number for an OH. Why? Because the extent of hydrogen bonding is the highest in case of an acid. That is what you can see over there. C double bond O is 1710. What about the OH bending? You will see at 938 centimeter inverse. Then another one characteristic feature is the C single bond O. C single bond O. Between 1000 to 1300 you can see. In this specifically you can see 1210 to 1320. This is the pattern. So remember these values. Whenever you have a carboxylic acid, first you should look into what? C double bond O at 1710, near 1710. Then OH, you will see it as a broad OH band between 2500 to 3300. Then you will get a C single bond O between 1210 to 1320. Then OH out of plane bending vibration at 920 centimeter. Same pattern is repeating here. OH, C double bond O, C single bond O, OH out of plane. See the absorption characteristics of this OH. Any compound which contains this C single bond O, it will show this pattern. Ester, ether, carboxylic acids, all of them will show this. Amides, a very interesting compound. The C double bond O, I hope you remember the first slide when I kept it. The C double bond O is reported the lowest for an amide. Why the lowest for an amide? Because nitrogen will exert a plus mesomeric effect, a plus resonance effect. Because of that, what happens? In case of an amide, the C double bond O will be the lowest. You are seeing here, 1640. But can you observe the type of the peak that you are getting here? C double bond O usually appears to be sharp peaks, but here you are getting broad peak, because here in fact two peaks are there. Can you see this? You are getting a broad peak because two peaks are there. How much ever you resolve, sometimes you get a broad peak here. One due to the C double bond O and another one due to NH bending vibration. You remember the first values we remembered? OH, CH, NH, not that NH, because that NH we are talking about a stretching NH. 3600, 3400 and 3000, OH, NH, CH. Here we are talking about the NH bending vibration. It comes between 1550, easy to remember. This is 1640 to 1670. Below that, 1640 to 1550, you will get this NH bending. So you are getting a broad peak over here. And this is the very important diagnostic band for an NH. Nitrogen is connected to two hydrogens. I hope you can remember. Nitrogen is connected to two hydrogens. So what will happen? Coupled vibration will be there. So you will be getting symmetric NH stretch and asymmetric NH stretch. You remember the base values? What did we learn for NH? The base value NH stretch 3600, then 3400 we learned. So around 3400, you will be getting two bands. You will be getting a split peak because of symmetrical and asymmetric stretch. You can see this particular band over here. See here, symmetric and asymmetric. Around 3400. That's why I put a broad value, 3100 to 3000. So you just keep in your mind 3400. That will be enough for you. Around 3400. See another amide. You get a typical bifurcated peak over here. Then you get an amide and an H band. You have it over here. Now come to the aldehydes. So what is that you see in the case of an aldehyde? In the case of an aldehyde, what you see here is C double bond O. It will be more when compared with that of 1715. Why you get a more? Because in case of a ketone, a methyl group is there which can reduce this C double bond O. But in case of an aldehyde, you don't have that. That is why you are getting it at higher. You will be getting C double bond O more than the base value, more than that of a ketone. Why? Because there is no alkyl group to exert a plus inductive effect over there. And because of that, what will happen? The carbonyl group is strengthened over here and you are getting it at higher wave number of 1725. More than a ketone, you will get it as an aldehyde. And what is the other feature that you are going to get in case of an aldehyde? See here, two peaks you are getting. Fermi resonance. Why the Fermi resonance happens? CH stretching of an aldehyde will couple with first overtone of the CH bending. I hope you remember. CH stretching will come at where? 2800. And CH bending will come where? 1400. So first overtone of CH bend means what? 2800. So one is 2720, another one is 2800, first overtone. So both will couple. And actually this overtone is not visible. But in this case, since it is an aldehyde, it will be visible. Why? Because it steals the intensity from CH stretching. That is what you see here. So aldehydes. This is a very important diagnostic band. These two only you can distinguish with an aldehyde. Here. See here. Here it is little more clear. Fermi resonance. You are getting two bands. You can make a note of what value I am telling you. Around 2850 and 2750. Around 2950 and 2850. 2850 and 2750. Around that, you can see two bands over here. And what is the other one? C double bond O. It will be more than 1715 because the bond is strengthened. Ester, C double bond O. Higher wave number. Why you are getting a higher wave number for C double bond over here? You see 1741. It is around 1725 to 1750. It will be more than 1715. It is more than that of the previous one. That is more than an aldehyde also. Why more than an aldehyde? Because oxygen is highly electronegative. It will pull the electrons. So because of that, what will happen? The bond will be highly strengthened and you will get a peak at very high wave number of 1741. And see the peak here, what peak you are getting? You are not getting any peak above 3000. Can you compare this? Any peaks are there above 3000? No. Why? Because only saturated portion is there. CH3, CH2, 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 CH2. You will not get any peaks above 3000. Suppose if the compound contained an alkene or an aromatic ring, then it would have shown peaks above 3000. Now it is showing below 3000 because only aliphatic portions are there. C double bond O is coming at 1741. And again you see a peak C single bond O. I hope you remember in the case of carboxylic acid, what do you have? C double bond O and single bond OH you have, no? So you have C single bond O. So here also you are having C single bond O. That is why you are getting a strong peak between, you remember the base value of C single bond O? C triple CH, OH, NH, CH, C triple bond N, C triple bond C, then C double bond O, C double bond C, C single bond O. In the base values, you remember, no? 1000 to 1100. Previously, I put one base value for you, 1000 to 1100. That 1000 to 1100 value range, if you can see, the C single bond O, you can see here as an intense peak over here. See here. 1000 to 1300. You can remember just one value, around 1100. That will serve the purpose. Around 1100. But this range I had given you, that's all. You will get a peak, intense peak. See here. The intensity of the C single bond O, see here. C double bond O, you see here. Then aliphatic, like a, if I can put a scale over here, now all the values will come after this. Anhydrates. What you can see in the case of anhydrates. C double bond O, C double bond O. This is going to have the highest strength. That is why you are having the C double bond O group, the most shifted at the highest frequency. Where you will get between 1800 to 1830 and 1740 to 1775. So among all the carbonyl containing compounds, this will be the compound which will show the highest value of C double bond O. I'll repeat the statement again. Among all the carbonyl containing functional groups, it will be the acid chloride and the acid anhydride which will be showing the highest value of C double bond O. And what will be the value? One asymmetric around 1800 to 1830 and one symmetric between 1740 to 1775. Why you are getting symmetric and asymmetric? Here two oxygens are there, right? The two oxygens come close away simultaneously. That is what we call it as in phase. That time you get what? Symmetric. It can be asymmetric. When one carbon-oxygen bond length is decreasing, another carbon-oxygen bond length can be increasing. That is what we call it as what? Asymmetric. Already we learned that asymmetric, you will get it at a higher wave number, and symmetric, you will be getting it at a lower wave number. So you are getting two patterns. One is 1800 to 1830, another one between 1740 to 1775. See, this will be the highest C double bond. And again, this is an aliphatic portion, no? It contains only CH3, CH2. That is why you are getting peaks only after 3000. CH, you will get it only below 3000. Nothing is above 3000. Why? Because there is no aromatic or alkenic portion. Then C single bond O. Can you see here a C single bond O? That is why you are getting intense absorption over here. You see an intense absorption. Ketone. Nothing to say, base value at 1715 you will get. Base value at 1715 ketone. So all this, so what and all we have seen so far, we have discussed about aromatic, we have discussed about alkenic, then we have discussed about the different functional groups which contain C double bond O. In case if the C double bond O is absent, then you search for an alcohol. So if it is an alcohol, where you will get? Again, you will get a broad OH, but now the OH will be shifted to higher wave number. Why the OH will be shifted to higher wave number? Because the extent of hydrogen bonding in case of an alcohol and a phenol is less. Whereas in case of a carboxylic acid, the hydrogen bonding is intense. That is why you are getting it near 3000. Whereas in case of an alcohol and a phenol, you will get the OH stretch at higher wave number. Around 3600 to 3650 you will get higher wave number. Or if it is a hydrogen bonded OH, you will be getting it between 3500 to 3200 you will be getting. So always alcohol and phenol, will show OH stretch at a higher wave number. Above 3600, 3600, 3650, like that you will show. It will show. Why? Extent of hydrogen bonding is very less. And you will not be getting any C double bond O peak also. Whereas in acid, you will be getting a C double bond O peak over here. Again, you see here, CH stretching vibrations you are getting below 3000. Why you are getting CH stretching vibration below 3000? Because only aliphatic is there. Alicyclic CH2 groups are there. Then OH bending. In the case of an acid also, you got an OH bending. Here also, you will get an OH bending, 971. What is the other peak? C single bond O. Ester, ether, all these cases you will see. 1070, 1000 to 1100, you will get a peak. Alcohol, OH, CH, CO. These are the three characteristic peak you will get for an alcohol. Amines, again, NH, what is the base value that we have learned? 3400. So around 3400, you will get peak over here. Here it will be between 3300 to 3500. Previously also we had seen this amine, NH2 group, where in case of an amide also we had seen. Here also you will see. Here also nitrogen is bonded to 2 hydrogen. So what you will get? You will get coupled vibration over here. Coupled vibration. So you will be getting asymmetric and symmetric. You are getting 2 peaks, 3438 and 3357. So 3438 represents what? Asymmetric. 3357 represents what? A symmetric one. Then here you can see 2 types of peaks you are getting. Can you see this particular portion? Below 3000 you are getting the peak, above 3000 you are getting the peak. So below 3000 if you are getting the peak, it represents CH stretching of aliphatic methyl group. Above 3000 if you are getting a 3036, that represents the CH stretch of an aromatic CH. So you are going to get 2 peaks over here. And carbon, nitrogen also. Ether. Ether, where you will be getting the peaks? Carbon, oxygen. You can see here a broad peak of CO. That is 1085 to 1150 you will be getting. Ether, carbon, oxygen stretching you will be getting. 1085 to 1150 you will be getting. And again you can see that all these stretching vibrations happens below 3000 only. Why? Because it is an aliphatic portion. Whereas in an aromatic ether, can you see above 2956, that is above 3000 also you are able to get a peak because aromatic CH will be showing. Again CO, you can see here, CO, 1000 to 1300 you are getting the peak. 1000 to 1300, C single bond O peak you will get. So I think with this I have completed giving data about the different types of the groups that will be present in a molecule. Madam, can you hear me, madam?
Yes, sir.
Now I would like to give some problems. How would you like the problems to be given? Should that mute
Yes,
be
sir,
open,
yes,
or how you would like to have it?
Yeah. Shall I unmute few
It is
more
up to you.
participants?
Whichever way you want, you can go for it.
Okay.
Because we have the problem solving now. I'll give them couple of spectrums wherein you will have a spectrum, you will have the compounds, they will try to match it and find out. So it is up to you.
Welcome, sir. Yeah.
Those who want to participate, maybe you can unmute them. Those who don't want to participate, you can mute them so that you will have very limited noise coming in.
Yeah.
And if you want to make it an interactive session, we can make it that way. Otherwise, let it be like the previous one, and I just go on giving them some time limit and I explain the things. You can tell
Yeah,
me.
anybody has raised the hand symbol, we will unmute for the particular.
So they can participate in it, and they can simultaneously, they can ask the doubts also in between.
Yes, sir.
So along with that clarification, it will go. Yeah.
Yeah.
It's an interactive session plus the problem solving session. If somebody is interested.
Yes, sure, sir. Yeah.
So once you give me the response, I will start with it. Once you ask me to start, I will start with it.
Yeah. I request all the participants. Now we are going to start the interactive session.
Along with the problem solving.
Hello.
Problem solving.
Yes, sir is going
Hello.
to post the.
Hello, sir.
Yeah. Yeah.
Hello.
Yes. Yes, yes, yes.
Yeah,
Hello,
you
yeah,
start.
this is Ranjan.
Yeah. Please tell me.
Right.
Can you please introduce yourself?
Actually,
Can you
sir,
please
you
introduce yourself?
always said that, yeah, myself, okay, myself, Dr. Ranjan Kumar Basak,
Okay.
and I have been a PhD student at IIT Kanpur.
Oh, great, sir. Yeah.
Hello.
Yeah, please.
So
Okay,
nice
okay.
to
So
hear
you
you, sir.
all okay. Thank you, ma'am, and very nice lecture, sir. Uh,
Thank you.
what I wanted to ask is, you always said that asymmetric stretch is
Yeah.
always greater than symmetric stretch.
Yeah.
Yeah, why is it so? May I get an idea of it?
Asymmetric stretch always requires
Why?
more energy. The energy that is spent, see, when we take a particular molecule, the energy that is spent
Yeah.
towards an asymmetric stretching is more when compared with that of a symmetric stretching. That is the reason.
Yeah,
Symmetry of the molecule is not there, and
that I
asymmetric
understand. But
stretching, yeah,
okay. Yeah. Why?
that is the reason. That
Why
is the
is it
reason.
so? Why more energy is required?
The
Okay.
strength
Fine.
of the
Fine. Fine.
bond, if you take in the
Acha,
case of an, yeah, the strength of the bond
yeah. Okay.
in
Okay.
case
Fine.
of
Fine.
an
Thank you.
asymmetric stretching, see, we can do it like this, like the polarity when you take in case of an asymmetric, the polarity of the bond
Yeah.
is not that much polarized, whereas in case of a symmetric one, the polarity, the polarization is very less. See, when you take a symmetric one and when you take a
Okay.
symmetrical
Yeah.
asymmetric molecule, in case of a symmetrical molecule, the polarity of the bond will be very less, or more of covalent feature will be there in that. Whereas when you go for an asymmetrical stretching, the polarity
Yeah.
is more, and because of that, the strength
Yeah.
of the bond also gets weakened over there. That is the reason why you have that asymmetric and symmetric.
Okay.
Yeah,
Thank you.
yeah,
Thank you,
yeah,
sir. Yeah. One more question, sir.
yeah,
Can hello?
yeah.
Can a
I'm able to hear you.
fingerprint
Please.
region? Okay.
Yes. Please tell me. Please ask the question. I'm able to hear you.
I think technical operator, please unmute to the particular participant.
Hello.
Yeah, I am
Yeah.
able to hear you, Dr. Ranjan.
Hello.
Yeah, I am able to hear you,
Yeah.
Dr. Ranjan.
Sir, what I wanted to ask is,
Ah,
yeah, can a fingerprint region of a
yes.
compound,
Yes.
when measured on two different instruments, be different? Can they be different? You can say a little shifted by, say,
Yes.
something like
Definitely.
5
Definitely. Definitely.
centimeter inverse or 7
Definitely.
cent.
Definitely.
Why?
Yes.
Why is it so? Why is it so? Is it because of the calibration problem or something else?
Calibration problem. Definitely. Because everything, if you standardize,
Okay.
exactly the two spectrums will match. But even a current variation, a voltage variation, the make of the instrument, everything can affect it, because it's going to be the most sensitive part. It represents the skeletal vibration of a molecule. So if everything is optimized, all are standardized, then only you will be getting the typical spectra repeating from one compound to another compound. The fingerprint region will be repeated. If all the things are left optimized, only you will be able to see that. Otherwise, you will not have that. All the other instrumental parameters, the
Okay.
sampling condition, everything is optimized. Then only you will be able to see that fingerprint region being coming back. That means it is reproduced. Yes.
Okay. That means each and every signal will
Yes.
be shifted by the same amount. Is it?
Yes. Definitely.
Okay.
Yeah.
Okay.
Definitely.
Okay.
Because it
Right.
will be uniformly. See, whatever parameters whatever conditions
Uniform.
you are going to apply, it will be
Okay.
applicable for all the bands. All the bands, it is going to be affected in a uniform manner. Definitely.
Uniform manner. Right.
Yeah.
Thank you. That's what I wanted to ask.
Okay.
Thank you,
Right.
sir. Sir, there are some
Thank you.
questions in the chat box also.
Chat box. Okay.
There are, sir.
Sir, how can
regarding,
should I stop
sir,
sharing it?
I'll ask, sir. I'll
Okay,
ask,
okay,
sir.
fine. Yeah.
So, from the participant Rajita and Vaishnavi,
Ah.
they asked a question: any software for IR spectral interpretation?
Definitely, it is there. I will show at the end of the slide. Possibly, if I want, if you want, I can show it now itself. I can stop the share and can put that. Please, just be a minute, sir. On the
Yes, sir. Yes, sir.
box, I will
Please.
just put it.
So I request the participants, please get ready to come up with the questions to clarify your doubts. It's an interactive session. Please utilize it. Our speaker is ready to clarify.
Yeah, these are some of the things.
Yes, sir, yes.
Just I was looking through and I found that some of the free softwares are there. Paid software is there. ACD Labs. I think this particular should be very familiar to all of you. You would probably using for drawing the structures, chem sketch and all. So there they provide it, but it is a paid one. And again, Protea. This is a free software. So certain free softwares are also there. Certain paid softwares are also there, where if you give the molecule, they will draw the structure for that spectrum and help us in finding out where the functional groups comes. It is possible.
Yes,
sir. It is possible.
Thank you, sir.
Yeah.
Thank you, sir. One more question, sir.
Yeah, please, sir.
Is it possible to analyze high molecular weight proteins by IR? This same question was asked by many people, sir.
Sir, please repeat.
Is it possible to analyze high molecular weight proteins by IR?
The main purpose of using an infrared spectroscopy is to find out the functional groups which are present in a molecule. So it does not have anything to do with the molecular weight. Irrespective of, provided you provide the ideal sampling conditions. I mean, you take care of the temperature, the technique what you are going to use, you will be able to detect it. The type of the bonds that exist, the type of the structure what it has got, you will be able to get an initial preliminary analysis of that particular compound. No problem with that.
Yes. Yes,
provided you have an ideal sampling technique for it.
Sir. And one more thing, sir.
Yeah.
In drug discovery, how this IR spectrum, at what stage it is useful, sir?
Okay. Can I just put a slide and explain to you this? I think I'll perhaps go for a slide.
Yes, sir.
I will just look into my presentation. Hopefully I should be having it. I think so.
Yes.
Just maybe 2 seconds. I will require to take it. Just a minute.
Yeah. Meanwhile, I will address the participants.
Yeah,
sir.
sure, madam. Sure.
Yeah. Thank you, Dr. Niranjan sir, for showing your interest to interact with our speaker. I think the session is more useful and it's more informative to all of us. And be ready now after completion of this interactive questionnaire. Our speaker is going to show the unknown spectra. Then get ready to answer for those questions. So whoever raise the hand symbol, immediately our operator will unmute to answer for those questions. Anybody? Meanwhile, I request one of our participants.
Madam, am I audible, madam? Am I audible, madam?
Yes, sir. Yes, sir.
See, participants, don't worry about the questions. Whether I am knowing or not, please post the question. So at least I can refer and get back to you. So please ask the questions. Whatever it is, you please ask the questions. So if I don't know, I will say I don't know and I will refer and get back to you. So whatever
Always,
things
sir,
are there.
We all are lifelong learners. There is no limit in that particular area. Definitely, it's knowledge. How to gain the knowledge by referring the books or articles. Meanwhile, I request one of our participants, Dr. Sirisha, Head Department of Analysis, Vagdevi College of Pharmacy, Warangal. Madam, can you express your opinion of today's session? I request our technical team, please unmute Dr. Sirisha Garu from Warangal, Vagdevi College. Dr. K. Sirisha. I request our technical team, please unmute to Dr. K. Sirisha. The participants are maybe in huge number, madam. They are
Yes,
searching.
madam.
Yeah.
Yeah.
Welcome, madam. Welcome.
Yes. Good afternoon. Good afternoon to the convener, Professor A. Sunita, the eminent speaker of today, Dr. P. Manoj Kumar, and to all the dignitaries and fellow participants. It's indeed a great pleasure to me to express my opinion on today's lecture. I am overwhelmed to listen to the excellent, elaborate, energetic, and enthusiastic talk of Dr. Manoj Kumar sir today. The presentation was quite interesting. It covered the intricate aspects of the topic very well. The teaching methodology was extraordinary, which could be assimilated easily. I am sure that not just young students and faculty, even senior faculty from various organizations around India, across India, like me, have learned many new things from this lecture. Thank you, sir, for enlightening us with your presence today. Finally, I thank Sunita madam and the organizers of Hindu College of Pharmacy for giving me this opportunity. My best wishes to you. Thank you once again.
Thank you, madam.
Thank you, Dr. K. Sirisha. I do accept, though we have 20 years experience in the analytical field, we have learned so many things from today's session, sir. I express my sincere gratitude to our speaker.
Thank you, madam. Thank you.
Manoj Kumar, sir. Sir, if it is ready, shall we continue?
Yeah. I'm just, is it
Please,
coming
sir.
in the slide, madam? It's coming in the slide, what I'm
Yes,
putting?
sir, it's connecting. It's connecting.
Connecting. Okay. Just a minute.
Okay. Sir, please share it in a new tab, I think. Sir.
Yeah.
Not
New
opening.
share.
Yeah, of course. Because the person who had asked the question, that typically that slide was there with me. That's why I thought I can.
Yeah, that we will
Nice.
give the clarification at the end of the session, sir.
End of.
Meanwhile,
Okay.
can we go for the...
Now is it? Stop share. Just a minute.
Sir, meanwhile, we will start that...
Just a minute, madam. I think I have it. And if it is there, I will be able to.
No problem, sir.
Yeah. So I think it is taking some time to.
Yes, sir.
Yeah. So I will rather. So maybe by the end of this session, I will do it.
Yes, sir.
Okay, sir.
Sir, I have a doubt, sir.
Yeah, please, madam.
Yes, sir. Sir, amongst the KBR pellet technique, which was used widely earlier, and the present ATR technique, which one do you recommend, sir?
ATR technique only, madam. This one
Always.
Always. Yeah. Definitely.
Because sometimes it's said that the KBR pellet technique gives excellent the sharpness, the resolution of the spectra is good with the ATR, with the KBR when compared with the ATR.
Yeah. But again, the problem.
Practically.
Yeah. That is right. But the most widely used and the accurate one will be the next one only.
Okay. Thank you.
I request the participants, anybody is showing interest to interact with our today's speaker.
Regarding the interpretation, if anything is there, please ask so that I can,
Student side, you
There is
please
a question
raise.
from Madam. There is a question from
Yeah.
Rajesh Kumar.
Yeah.
How this IR spectra interpretation useful, especially in characterization of drugs from the plant extracts?
Plant extracts, okay.
Yes,
See,
sir. Yes, sir.
I'll come back to the slide and I'll just a minute. Just,
Okay, sir. Okay.
I'll just keep my slide ready so that I can. I think my slide is visible now, madam. My slide is visible
Yes, sir.
now.
Yes,
Yes,
yes, sir.
Okay. Okay. So here is where we stopped. I think so. Yeah. Okay. As far as the IR spectroscopy is considered, it's not an individual method. It has to be used in conjunction with other spectroscopic methods, like any other spectroscopic method. See, yesterday when the speaker was telling, he was trying to couple the IR and NMR together. So you get a lot of information. So IR spectroscopy, it helps us in identifying the functional groups. So as we discussed now, whatever may be the type of the functional group that is going to be present in your compound, it will be very much evident from the IR spectroscopy. And it can be used as a supportive tool along with the nuclear magnetic resonance spectroscopy and the mass spectrum, what we are getting. And you will get to know about the, as we just discussed now, the aliphatic nature of the molecule, or it contains aromatic nature, whether any double bonds are present, and what type of substitution occur in that. And basically, it's a functional group analysis that we do in the case of IR spectroscopy. So it's a supporting tool for the natural products discovery. Definitely, it helps over there. Preliminary, whether a particular reaction has happened or not. For example, you are doing the extraction process, and during the process of extraction, you expect a particular active constituent to be coming, and you suspect that okay, these groups should be there. So rather than going for any other costlier methods, you can conduct a pilot study wherein you extract the compound and you do the IR spectral analysis and you confirm whether this compound is there or not, and then you can proceed further. So definitely in the natural product discovery, it helps you in optimizing a particular technique, but never you can say that it is a complete method. It's not a complete method. It has to be used in conjunction with other spectroscopic methods. Hopefully, I answered the question. I think I have answered the question.
Yes, sir. Yes, sir.
It helps. It helps. Is it? Can we go for
Yes.
it? Or any other questions
Yes,
are there? Any other questions are there?
No, sir. Please proceed for interpretation problems.
Okay. Okay. Fine. Okay, so all that we have learned so far is about how different functional groups show themselves up in the IR spectrum. So here we are having the C double bond O peak. If it is there, it can be an anhydride, acid, amide, ester, and aldehyde. And on the other hand, if it is a ketone, if all these groups are not there, then it can be a ketone. If there is no C double bond O group, then the possibility is for an alcohol, amine, ether, nitrile, alkene, aromatic nitro compounds, and halides. So this is also very important. You can calculate the unsaturation number of a compound. Please make a note of it, those who are interested. You can calculate the number of rings in a compound, whether it is double bond or triple bond, whether it contains an aromatic ring. All these informations, you will get it by calculating the unsaturation number. You have to use this formula like C plus 1 minus 0.5 into X minus N, where X represents the number of monovalent elements and N represents the number of trivalent elements. So there you get it. Let us apply in case of an ethane. So in ethane, if you apply the number of carbon atoms, you know it will be 2 plus 1 minus 0.5 into X. X represents the number of monovalent elements. So in the case of ethane, you know that 6 hydrogens are present, minus 0. 0 means the number of trivalent elements is 0. So all the things put together will be equal to 0. And all of us know that ethane is a completely saturated molecule. And similarly, in the case of cycloalkanes, if you put the same formula, finally you get the value of 1. And you know that it is a ring structure. It has got a ring. So you are able to find out the particular aspect making use of this unsaturation number. In case of benzene, you know, the U value will be equal to 4. You put the value of carbon plus 1 minus 0.5 into X. You know that benzene contains 6 hydrogens. No trivalent elements are there. Finally, it is 4. So what are the three? What is that? What does that 4 signify? You got one ring in it, 1. Then 3 double bonds. So 3 plus 1 is equal to 4. So this helps us a lot in interpreting the structure of the compound. I will not go to this slide, rather I will make use of this slide. So whenever you get an IR spectrum, please proceed in the following manner. You divide your spectrum into 5 zones. The first zone, please make a note of this. This would be very helpful. Please make a first note of it. The note of the first zone. What and all bands you will get in the first zone? Already we discussed only very limited number of functional groups, so we can apply to that. So this particular chart will go on, has to be corrected as new and new functional groups come in. But more or less the zones will remain the same. But what and all groups will come in a particular zone will vary, depending upon the new and newer functional groups which you are going to study. So here in the first zone, you will be getting the following groups. Amide NH stretching. If you want, you can make a note of it. See, amide or amine NH stretch. Don't see these values. Don't memorize these values because already we have seen in the slides. Amide or amine NH value, alkynic CH, alcoholic OH. You can remember easily alkynic triple bond CH. Alkynic CH will be showing the highest stretching vibrational frequency in this region, zone 1. Or it is the CH of the alkane which will be showing the highest frequency. CH of the alkane will be showing the highest frequency. Then coming to zone 2, if you take the zone 2, you will get alkenic CH and aromatic CH, alkenic CH and aromatic CH above 3000 to 3100 you will be getting, and below 3000 you will be getting all the aldehydic CH you will be getting. Already we have learned that 2850 to 2750 you will be getting aldehydic CH. You can see here the zone 2. Don't remember these values, we can easily do it later on. So you can see here alkenic CH as well as aryl CH, they will come above 3000, and below 3000 these are the other 2 CHs, which is that the methylene CH2, the methyl CH3 or the methine CH. All that CH will come below 3000. Please make a note of it. So above CH, above 3000 you will get the CH corresponding to a benzene or an aromatic compound, and the CH corresponding to an alkene. And below 3000 you will be getting corresponding to CH3, CH2, then CH, that is methyl, methine, methylene, CH stretch you will be getting. And below that you will be getting Fermi resonance. Already we learned about it. Around 2 peaks you will be getting, around 2850 and around 2750. See, I have put here, these values will vary depending upon the different types of textbooks that we are following. This, because this is actually Hardinger book I have followed, and there they have put on value. If you follow Silverstein, variations will be there from textbooks to textbooks. So don't need to remember exactly these values. For the sake of convenience, you can remember it around 2850 and 2750 you can remember it. Then carboxylic acid OH, it will center near 3000. See the difference here. This particular slide, you see the difference. What you are having here, alcoholic OH. Madam, my cursor is visible. Sir, my cursor is visible. My cursor, is it visible, sir, in the slide? Hello?
Yes, sir.
My cursor, is it visible, madam?
Yes, yes.
Yes. So alcoholic OH, you see it is occurring at a higher wave number. Whereas carboxylic acid OH, it is coming at a lower wave number. See the difference. Both are OH, but one is seen in zone 1, another one is seen in zone 2. Similarly, you go for the zone 3. Very less number of bands. Only 2 bands, most probably you can see here. Third zone, C triple bond N and C triple bond C. C triple bond N and C triple bond C. You will get. This, you will not get a fourth zone, another important zone. You will get all C double bond over here, C double bond O. You will get it over here. All the C double bond O, you will get ketonic, ester, aldehyde, carboxylic acid, amide. Then the last zone is the 5th zone you are getting here. this is the place where you really can find out whether the compound is aromatic or alkenic, making use of this. You will get multiple bands in this region corresponding to CH bending vibration if the compound is aromatic or if the compound is alkenic in nature, unsaturated in nature. So these 5 zones, you please have it in your mind, which will help us in the further interpretation exercises. So the first one, as I told you, you can check the presence of alcoholic OH, alkynic CH, and amine. And the second zone, that is this zone, it gives you information regarding the CH of an aryl or the vinyl above 3000, and below 3000 you will have alkyl and aldehyde. And obscuring all this, you will have the carboxylic acid OH coming between 2500 to 3000. And zone 3, you will be getting relatively very less number of bands, C triple bond C and C triple bond N. Then zone 4, you will be getting ketonic, ester, and all the carbonyl functional groups you will be getting. And zone 5, you will be getting multiple bands arising out of C double bond C stretching vibration and C double bond C bending vibration. So all these zones, we are talking only about the stretching frequencies, diagnostic bands. We are not looking into the bending. So bending will be adding support to our observations here. That is what. So here I am applying that particular concept. So the first zone, you can see there is no peaks. Second zone, if I am applying here, of course, you can see the peaks below 3000. It tells me that it contains an alkylic portion. That means a saturated CH3, CH2, CH groups can be there. Sometimes it can be alicyclic also. It can be alicyclic also, alkylic or alicyclic. This portion again, you come to the third zone. C triple bond C, C triple bond N. It should occur at this region, 2250 and 2150. 2250 and 2150. You cannot see any bands there. C double bond O, definitely it is there, 1500, 1700. So it tells me that the compound is aliphatic in nature. It contains a carbonyl group. Further, I can search for the diagnostic bands which supports this. Once again, when I say it is not an alkenic or aromatic, my observation is strengthened by this, what I am seeing here. In the zone 5, if I can see, it is a comparatively neat spectrum. I don't have any bands over here. You can see there is no band I am getting. Between 1585 to 1600 or 1400 to 1500. This is 1400. You don't see much of peaks here. No peaks at all. So see the zones when I'm applying. This is what I'm telling. And so a ketone, a C double bond O group and aliphatic. See, this is the compound. So this is how we can do the analysis. So now I'm going to give the experiments, and madam, so all will be participating, or how the thing will be? Like I have put the spectrum here, and you need to identify the compound. Excuse me, madam. Hello. Madam, can you hear me?
Yes, sir.
Will they be answering, or how things can go about? I put the spectrum now. They need to identify the compound. They can.
Okay.
So let them raise the hands they want, and we can wait for 1 minute, and then I will tell the answer.
Yeah. Meanwhile, I request Hassan Kunwal. He wants to interact with you, sir.
Sure, ma'am. Sure.
I request our technical operator, please unmute. Hassan Kunwal.
Good afternoon, sir, and good afternoon, all the organizers.
Yeah.
The presentation was very much impressive and informative.
Yeah.
Actually, I'm a PhD research scholar working in Kakatiya University.
Oh, great.
My question is whether we can develop a method using IR.
For what? For which one?
Method development and validation by using IR technique.
Definitely.
It
is one of the application of the IR spectroscopy is in quantitative analysis also. But again, the practical application of it will be very less, because we have got so many other sensitive methods also now. So how far the application process, we need to check it. Basically, as I have already mentioned in the very beginning, IR spectroscopy is a useful method for functional group analysis. That is where it is widely being used, rather than any other quantitative analysis or method development. So that is what.
Sir, but in case of biosimilar drugs,
yes,
which are having 935 amino acids, it means that it is having many different functional groups.
Yes. Yes.
So will it give a clear IR spectra?
Functional groups analysis, definitely. See, again, there are certain limitations of the infrared spectroscopy. For example, as we had seen, some of the bands, they can overlap. For example, you expect for a particular functional group, but like I had put you in the case of amide, you are expecting a C double bond O group at 1640 to 1670. And the same place only you are getting for an NH bending also. That is coming between 1550 to 1640. So you can interpret in two ways. You can interpret that it is a C double bond of group of an amide, or you can interpret it as C double or just a C double bond of group only. So sometimes when so many functional groups are there, and wherein the functional group will be showing for at the more or less the same region, then we have to search for other diagnostic bands also. But
Okay, sir.
it is definitely an analytical tool, and it can tell us the functional group present in our compound. It is a concrete evidence for that. And especially it will be much strengthened, as you already told. Suppose if you have a non-compound, if you have a standard reference compound with you, and if you can take that spectra and you suspect your compound to be that, you can compare the two spectrums and definitely you can say that this compound is the other one. In case of a novel compound, identifying the functional groups, definitely it is a very supporting evidence. But for quantitative analysis, you have to think about it. Then only you can proceed, because so many other factors will ultimately decide the quality of the experiment that you are going to perform.
Okay, sir. Thank you, sir. Sir, can you please share your email ID?
I will put towards the end of the presentation. Is it okay?
Yeah.
I have put a slide for that. In the thank you slide, I have put it. Last thank you, I have put my mail ID also.
Thank you very much, sir, for your
Thank you.
outstanding explanation.
Thank you for the question. Thank you for the question.
Welcome.
Okay.
One more participant is waiting, sir.
Yeah, please.
Ananta Prasad garu.
Oh, sure.
Welcome,
Please,
sir.
please
Ananta
unmute.
Prasad garu.
Prasad,
Hello.
sir.
Hello.
Hello.
Yeah, it's audible, sir.
Sir, I am able to hear you, sir. Please, sir.
Okay. So, good afternoon, sir. Sir,
Good afternoon, sir.
informative session, sir.
Good afternoon, sir.
Sir, can you able to hear me?
I am able to hear you, sir. I am able to hear you. Please.
Sir, my question is, in the case of structural illustration, is generally we take the IR, NMR, mass like this, where we take the multiple analysis. Right? Then only we are going for confirming the structural illustration. Okay.
Definitely.
But in the case of any other one method to determine the structural illustration perfectly, completely. Any software related to this one.
Sir, I am not able to hear you properly.
Sir, that I will clarify it. At the last day of FDP program, there is a session for entire overall spectral interpretation, how to elucidate the molecular formula and structure.
Yes.
By interpreting all IR, NMR, mass, including UVC13. Today's session is exclusively for IR. You please ask the questions in this regard. So I think there is no software to elucidate the entire structure.
Madam, can I just add on in this?
Yeah,
something in
please,
this?
please.
It is really many a times what happens. I just it is my remark in this particular case, because we have a wide audience and we have academicians in this. Many a times they interpret in a wrong manner, and really the scholars are getting confused out of this.
Yes.
Because many of the instruments, they have got the softwares being implanted in it and tells the probable structure of the compound, where the exact reality may be, it will be like the compound never matches that spectrum. That is the actual reality. The softwares are there, plenty numbers of softwares are there, but you really require a manual interpretation to finally arrive at the structure of the compound. Because as sir has correctly said, Ananta Prasad sir has correctly said, you need to put all these spectroscopic techniques together, and then only you can finally confirm the structure of a compound. Either IR alone or NMR alone or mass alone will not do. Even in mass itself, you have got high resolution mass spectroscopy, where you can find out the molecular weight of a compound to the fourth or the fifth decimal place, and you can be sure about the structure of the compound. So it is a combination of C13, proton, X-ray diffraction. One compound, maybe in a very simple structure, you will be able to identify. applying IR and NMR alone. But when you have complex structures, you need to put all the spectroscopic methods together. And since today's presentation is on IR, I'm just focusing on the functional group analysis. That is what.
The main motto of this entire FDP program is day by day we have to acquire the knowledge at a particular area. Then at the end of the program, I hope all the participants can acquire sufficient knowledge to interpret the all over the spectra to elucidate the structure and molecular.
Definitely, madam.
That is
IR
actually
spectrum,
my motto, sir.
Yeah, I'm sorry to intervene in between. IR spectrum, what I practically or what I personally experience is the more number of spectrums you go on interpreting, the more number of spectrums. You go through a lot of textbooks, every IR spectrum and structure when you correlate, finally, but one very important thing is there are 4 aspects to be taken care of. The instrument should be properly calibrated. Sampling conditions has to be specified. The compound should have reasonable purity. All these conditions, if it can be maintained, and if a spectrum can be taken, you can tell the type of the functional group present in the compound. Definitely, that is for sure. But you have to go on analyzing spectrums and spectrums. Thousands of spectrums, if you go through, definitely it gives a lot of information. To support the other spectroscopic techniques, it's a very versatile tool.
Yes, sir.
Thank you, sir. Thank you very much.
Thank you very much, sir. Thank you very much. Okay.
So regarding displayed spectrum, one participant gave an answer that the displayed structure is benzonitrile.
Benzonitrile. Okay, very nice, very nice, very nice.
Yeah,
can I? Okay. So I think I would. It's very nice. So first of all, congratulations to that person who has tried to identify it. I'm so happy that by this presentation the participants are participating. It's a positive.
Definitely, sir.
I request technical operator, please unmute to that participant because we have to appreciate our efforts.
Yes, efforts are very, very important. Rather than looking into the right answer and the wrong answer, the efforts are which counts.
Efforts are, yes, sir.
Yeah, that's what.
So
because somebody may be very new to this area and somebody may be having a lot of experience. Yeah.
Sridhar, unmute Vijayalakshmi. Koyagura Vijayalakshmi.
Okay.
Yeah, so Vijayalakshmi, number of participants are there. It takes a little bit time to identify.
I think if they raise the hands, I think maybe we are able to identify. Maybe. Okay. Anyway, can I proceed with the answer, madam? Can I proceed with the answer?
Yes, yes, sir.
See, these are the places where you are literally getting a problem because see here you have a portion and the spectrum is not so clear also. So here you have a confusion because above 3000, I told you, if you get some peaks, it indicates aromatic nature. Okay. It indicates aromatic. So here you're getting some peaks. I think possibly because of that, the person has got some impression that it can be a benzonitrile. But I really appreciate because she could interpret the C triple bond N. She could
at
see
least
that.
Made attempt.
Yeah, not an attempt, madam. It's really a great attempt because 1667 to 2000, you get a C triple bond N peak over there. This is coming in the zone 3 and you are able to identify it. That's great thing. And here, so people when they're responding, no, I will be able to put my views also into this. And you are getting peaks below 3000. Can you see the peaks below 3000? Can you see the peaks below 3000? It tells it is an aliphatic compound and it contains a C triple bond N. Confusing one is benzonitrile, whether it can be, because you have a peaks over here. So my simple question is, how my claim is it has to be a propane nitrile. It has to be an aliphatic nitrile. But somebody will argue with me stating that you have got peaks over here, so why can't the compound be benzonitrile? What will be the solution to this? If somebody can answer, I will be happy about that. My question is very clear. I am telling this compound is propane nitrile because you have got aliphatic CH over here and a C triple bond N here. Then obviously somebody can object stating that here you have some peaks. Above 3000 you have some peaks. So why can't it be benzonitrile?
Sir, one person has answered, Vasanta Amruta.
Please, madam. Can they just speak out what is their opinion? So I would like to have an interaction and then go. That is what I feel. Yeah.
I
What could be the
request
possible
our
answer?
technical team, please unmute Vasanta.
Is it okay, madam? We proceed in this way. Is it okay?
Yeah, our session is over. So if participants are really showing interest,
Yeah,
we
definitely,
have
definitely. That is what.
interactive
So
session.
we'd like to have an interaction and then we can move.
Yeah.
Those who are really interested, they can stay on. Yeah.
Madam, I invited Vasanta Amruta, madam.
Okay.
Yeah. Vasanta Amruta, please.
Madam.
Feel free to talk. Yeah.
Yeah. It's a free conversation. Nothing to feel that it is right or wrong or something like that. No, it's a mutual discussion. So my doubts also will be cleared. That is.
We all are learning. Still how to learn so many things. Nobody is expert here.
Good afternoon, sir.
Good afternoon, madam.
Tell me, madam.
Yeah, it's audible. Welcome.
Sir, above 2000 peak.
Above 3000, no? Above 3000. Yeah.
That's why I have identified as nitrile group. That is.
Okay, madam. Okay.
Peaks are
yeah. A very nice observation.
Around 1500, below 1500, no? That's why aliphatic CH peaks.
So what is your final conclusion? What is your final conclusion?
Propane nitrile, sir.
Propane nitrile. Very nice. Very nice.
She has given answer, sir, previously before your explanation.
Okay,
she mentioned number 2. Then we didn't focus it on.
Yeah. So this is the one. Because the entire session is about solving the problems in vibrational spectroscopy. So that is what we are trying to focus now. In this session, that is what I would like to specifically focus on that topic. So you have a doubt whether it is benzonitrile. So immediately what you should do, when you have that doubt, you just observe the spectrum and try to identify whether there is any diagnostic band which supports that it is an aromatic region. You will not see that. I already mentioned that between 1585 to 1600 and 1400 to 1500, you should be getting peaks. And here, it is comparatively a very neat spectrum that you are having. So, and not only that, if it is a benzonitrile, then see the type of substitution should be mono. Then you should be getting OH out of plane bending vibration also should be there. Suppose if it is a mono substituted, you should be getting 2 peaks. I think while I was going through the slide, I was telling you will be getting 2 peaks, one at 700 and another one at 750. That also is missing in this. Can you see that? This is 500, 600, 750 region and all, you are not having much of this. So, see, it's propane nitrate. Congrats to the person who has told the answer, and she was descriptive also. Thank you for that.
Yes, sir.
Thank you for that.
And one more participant is want to interact with you, sir.
Yeah, definitely. Please.
So please, Sridhar, Rajiv Kumar Badkaria, unmute. Rajiv Kumar Badkaria.
Yes, sir, unmuted, sir.
Yeah.
Mr. Rajiv Kumar, please.
Sir, Rajiv Kumar, sir, please unmute your mic.
Already we have unmuted you. Please talk, sir.
Hello.
Yes, I'm able to hear you, sir. Can you please introduce yourself, sir?
Yes.
Yourself.
Sir, you please unmute yourself, sir. Rajiv Kumar Garu. Yeah, please tell me, sir.
Please tell, sir. Sir, Rajiv Kumar, sir, I am able to hear you, sir. You can proceed with your question.
I think we are not getting his voice.
Hello.
Once again.
Sir, please.
Mr. Rajiv.
Mr. Rajiv, I am able to hear you.
Hello, Rajiv Kumar, sir. Hello.
Okay, sir. We'll proceed for another participant.
Okay. Please, sir. Please
unmute Kavita, madam.
Yes, sir,
welcome,
unmuted,
Kavita
sir.
Garu.
Hello, Kavita madam.
Hello, Kavita madam.
Okay, sir. We'll go for
Sir,
next
shall
compound.
shall we go for next spectra, sir?
Yeah,
Meanwhile?
definitely, madam. Definitely, madam. Maybe some technical difficulty. Maybe the net connectivity for the participants. Maybe
Yes.
that is the reason.
Yeah.
Okay. Can we identify this spectrum? It's a very, very like a very impressive spectrum. I felt because very easy to apply what we have learned now. Can somebody identify this compound? It's a new one. You got typical pattern of the peaks here, comparatively neater spectrum. Can anybody identify this? Don't worry about the answers because here we are in net and nobody can see the faces also. So no problem. You can come out with your answers. So don't worry about the answers.
Sir, Sharath Reddy has given the answer.
Very nice.
Acetophenone.
Very good, very good, very good, very good.
Acetophenone.
Acetophenone. Okay, okay,
Yeah.
okay. Can I have him interacting with me? Can I just have from him like why he feels that it is acetophenone? Is it possible? Yeah.
Yes, it's possible, but whether they are going to show the interest. Sharath Reddy.
Acetophenone.
Yeah. I request
Unmuted.
Sridhar.
Yeah, unmuted, madam.
Sharath Reddy, please share your opinion.
If you want. If he's hesitant, okay, it's okay. No problem.
Sharath Reddy. Sir,
Sharath
another
Reddy.
participant.
Oh, definitely, madam. We'll give chance for everybody. Yeah, definitely, definitely. Another person is telling isopropyl alcohol. Okay, let them. Can they say why they feel that way? Why they feel that way? Can I just find out?
Sridhar Kirtana.
Kirtana Divya.
Oh, please, madam.
Kirtana is unmuted.
Okay.
Kirtana, please feel free to express.
Because till now it was my session, and now it is a session of the audience. In fact. Yeah, because they can say why they feel it that way. That is what.
Yes, sir. Yes, sir.
Kirtana, madam, please unmute your mic.
Good morning, sir.
Good morning, madam. Good morning, madam.
Myself, Kirtana from Osmania University. I'm pursuing my MSc, sir.
Great, madam.
Very
Great.
good.
Yeah.
Welcome.
So can you just tell me like why you feel it is an isopropyl alcohol? Why you say that it is an isopropyl alcohol? What makes you to say that it is an isopropyl alcohol?
Because we see a band at 3,300. So it indicates the presence of hydroxyl group.
Very good. Excellent, madam.
And around 3,000, we are having aliphatic CH stretching.
Okay.
So based on that, I came to conclusion that it might be isopropyl alcohol.
Okay. So why you are not telling it is a propargyl alcohol?
Because we did not find C triple bond C stretching.
Very nice. Excellent, madam. And why you are not telling it is a butanoic acid?
We don't have C double bond was stretch.
C double bond was stretch. Excellent. Yeah. So the answer is correct. It's an isopropyl alcohol. See, if you observe the first zone, as we have already seen, the OH group, you will get it at a higher wave number. And OH group, you will not get it around 3000. OH group around 3000, if you get, you say it is an acid. OH group around this 3600 region, it always indicates an alcohol. But again, you have two problems. Two types of alcohols you have. One is propargyl and another one is isopropyl. It is not a propargyl alcohol because you don't get any prominent C triple bond C in the third zone. That means you are not getting it at 2250 or 2150. And again, it is an aliphatic one. You can see here very precisely the vibrations you are getting below 3000. So the answer is correct. Isopropyl alcohol. Sure. It's fine, madam. Very nice.
Sir,
I go for the next one. So anybody is having any doubts about this? Anybody feels like asking any doubts about this? If they are in chat or something, they can interact now. If anybody. Or the question, if somebody has put it, it can be passed on to me. If they have put any question in the chat, that can be passed on to me also.
Yes, sir.
So the moderator
sir, one more participant has given the answer. Seventh one. Propargyl alcohol.
Yeah. That is what C triple bond C you will get as a peak over here.
I request Sridhar, please mute the rest of the participants. Please avoid noise. Yeah. Sir, please continue, sir.
So in the case, his observation is very correct, propargyl alcohol. But the problem what you face here is C triple bond C, you cannot see it as a peak over here. Since C triple bond C you are not able to see, you can definitely delete this option. That is, you can fix it to be isopropyl alcohol only. Because you cannot assume this, because C triple bond C peak is not there. Here only I am telling you should it comes out of examining lot of spectrums. When you take 100 spectrums with C triple bond C, then you will come to know how a C triple bond C will look like. It is easy for us to remember the values of C triple bond C, but exactly how C triple bond C looks like in a real spectrum, out of experience we will get it. But his observation is really to be appreciated, because he has found out that OH group. And not only that, he has found out that it is an alcohol also. Great. Great thing.
Excellent, sir. Excellent.
Yeah, very good, madam. Can I go for the next one, madam? Can I go for the next one?
Yes, sir. Please.
Yeah.
Quite interesting.
This is like a photograph of that compound. I have put a photograph of that compound.
Okay.
Can anybody identify this? Can anyone identify this compound? Anybody?
We will see the charts. Maybe it takes.
Madam, finally we will declare also. Finally, we will declare the person who is telling the maximum number of correct answers. In this session, we will have that also.
Yeah. Sure,
in the
sir.
chat, if you see, we will come to know who is telling the highest number of answers. For that, we should appreciate, and who is telling the correct also.
Yes, sir.
So somebody came with the answer for this?
Not a... Sir, meanwhile, you please address the rest of the participants about the software. I think already it's covered now.
It's covered.
Drug discovery, related to drug discovery.
Drug discovery. Drug discovery, I can take a small example. So for example, you are taking a compound with a nitro group. So by analyzing the IR spectrum, you will come to know the symmetrical and asymmetric nitro group stretching. So I am doing the reduction of this, and I am going to take the final compound. I have an NO2 group. I am doing the reduction. I am getting an amino group. So while taking that particular compound and I am subjecting it to IR spectroscopical analysis, two things will tell me whether the particular reaction has happened or not. Two things means the nitro group, I already told that the asymmetric and symmetrical stretching you will get for a nitro compound. That will totally disappear, because the compound I have converted a nitro compound to amino compound. So somebody asked me the question, how it will be helpful in the synthesis. So I am answering for that. So let us assume that you have a starting compound with nitro group. I am taking the spectrum of it. It will show two stretching vibrations. One is asymmetric and another one symmetric. One around 1300 to 1390 and another one between 1500 to 1600. Symmetric and asymmetric NO2 group. But the same compound, when I am doing a reduction with it, the final compound will not have an NO2 group. It will have only amino group. So when I take the spectrum of that compound, I can see an NH2 stretching. So that confirms that amino group has been formed. And similarly, the final compound will not show any NO2 stretching also. Like this, every step when you do the IR spectral analysis, you can come to know whether the reaction has happened or not. So you take a particular functional group, check for its presence. If that functional group is not changing, if the functional group is showing in the IR spectrum, then you can be sure that the reaction has not happened. Whereas the functional group is changing, then a new functional group has been identified. You can say the reaction has happened. So that way it will help in the synthesis. I hope I am clear with my...
Yes.
Yeah. So that is how it helps in the synthetic.
Sir,
Any answers,
we received 3 different answers.
Very good.
I think two of them given first compound.
Acetone. Okay.
Yeah. Other person has mentioned methyl benzoate. The other
methyl
person,
benzoate. Very good.
The other member mentioned benzonitride.
Okay. And I want you should give some appreciation to the person who told benzonitride.
Benzonitride.
It's a correct answer.
Three members have given. Sir.
Excellent. Excellent. Very nice. Very nice.
Yeah, I would like to mention their names.
You can call their names, madam. You can call their names.
Vasant Amruta, A. Kirtana, and Vijaya Lakshmi K.
Very nice. Congrats.
Yeah.
Because literally that is the reason why I told this is a photograph. And also appreciations to others also who attempted. Because that is very, very important. Attempting is also very, very important, because when you know something only you can apply it. Because appreciations to those participants also who took part in this. Am I able to hear? You are able to hear me, madam? Am I audible?
Yeah, it's audible, sir. Sir, one more thing. Let us give clarity for the people who have given the answer for fourth compound. They interpreted it may be a fourth one. The other two have mentioned a first compound. So
yeah, I'm going to explain about it. I'm going to explain. See, when you see this particular structure, I have put a red line over here. It is Lakshman Rekha to identify whether a compound is aliphatic or aromatic. Please take care of that. Or let us follow systematic analysis. In this particular area, you cannot see any peaks. So you can forget about alkynes, you can forget about amines, you can forget about amides. Now we are coming to the second zone, where you have a danger line. So below this, you don't have any peaks at all, which clearly tells that it is not an aliphatic compound. It can be only an aromatic compound. So somebody will argue with me stating that why you are not considering it as an aliphatic compound. These peaks you can consider. No. Again, I will tell you, go to this particular area. 1585 to 600 and 1400 to 500. You can see plenty of peaks are over here. 2 peaks you can see. So it adds weightage to my observation that the compound is aromatic in nature. So that part I can confirm it. Aromatic in nature. Sure about it. That I already mentioned. The third zone, it is very different. It will have 2 peaks. C triple bond N and C triple bond C only will show. And see the intensity of the peak that you are getting. It's a typical C triple bond N. Because I already mentioned there is a big difference between the electronegativity of carbon and nitrogen. It shows high dipole moment. So it will show intense absorption, a strong absorption. This is very much characteristic of C triple bond N. So it has to be benzonitrile. And further, you can add all supporting evidences to this. It is a monosubstituted. Benzonitrile is a monosubstituted. So if it is monosubstituted, you should definitely be getting CH out of plane bending vibrations. CH out of plane bending vibrations. For a mono, I told you, you will be getting 2 peaks between 700 and 750. This is 500, this is 600, this is 700. So between 700 and 750, you are getting 2 peaks, which tells that it is monosubstituted. And one more supporting. See here the pattern of the bands that you are getting. Can you see a pattern here? Between 1667 to 2000, can you see a pattern here? It is also identical with that of an monosubstituted aromatic compound. So all this invariably tells that it is benzonitrile. And that is the reason why I did not go for acetone. Acetone, why you are not concluding? Because if it was acetone, you should have got a C double bond. So all those who answered as acetone, it is very good that you attempted, but it will be better if you know reason why it is not so that you can avoid it the next time. C double bond, it will show a peak at 1715. You are not getting, see 1500, 1600. See this peak? See this peak? It is coming at 1600. Above 1600, no peaks. It is a very neat spectrum. C double bond should show a peak here. Since you are not getting, you can confidently say it is not an acetone. Not only it is not an acetone, it's not benzaldehyde, it's not butanoic acid, it's not acetophenone, it is not methyl benzoate also. That is the reason why I am putting my stress on benzonite. Can I go to the next slide?
Yes, sir.
Okay. What about
sir,
this?
Before that, please
tell me, madam. No problem. Please tell me, madam.
After giving the spectra, I want to appreciate the participants who have given the right
definitely.
answer.
I think probably this also they'll be able to do it. I think so.
Yeah.
This is again a photograph of my compound. This is much clear. Very much clear. It's a photograph. Maybe I can add some clues. You can see it around 3000.
Okay.
Then this particular band you can never miss in the spectrum. You can never miss in the spectrum. You can.
We got the answer. Acetone. Somebody has given the answer acetone. Somebody has given answer propagyl alcohol.
Okay.
Seventh one. Two
And
of them given.
any other
aceto.
answers, madam? Any other answers?
Eighth
Any other
one.
answers?
Benzaldehyde.
Okay. Any other answers?
I will see the chat.
Benzonitrile.
Benzonitrile. Okay.
Yeah.
Any other answers?
One of them mentioned carboxylic acid.
Which acid, madam? What is the number?
Number they didn't mention.
Butanoic acid, huh? Butanoic acid.
Maybe.
Acetophenone also mentioned.
Sir, we almost covering
Almost all.
Okay, congratulations to the person who has said butanoic acid. Congratulations to the person who has said butanoic acid.
Kalyan Varma.
I don't know whether 8 people are there and putting 8 different names. I don't know that.
Sir, nobody knows. Kalyan Varma has given the answer butanoic acid.
Excellent. It is correct. It is a correct answer. Butanoic acid. Excellent. Can I have that person interacting, madam? Is it possible?
Yeah,
is it possible?
we'll try. Yeah, let us try, sir. I request Sridhar, please unmute.
Yeah, unmuted, madam.
Yeah. Is that Kalyan Varma?
If we can substantiate with this answer, butanoic acid.
Kalyan Varma.
If it was a live session, I would have given some prize to that person. But now we are over the net, so that
Yes,
is a
sir.
limitation for us.
Definitely, sir. If I will send one surprise gift to him.
Definitely, definitely to him, to all the people who are answering, some sort of appreciation we need to give.
Sure, sir. Sure, we will encourage. Then only the session will be fulfilled. Kalyan Varma, I think he's not on the line.
Can I continue, madam?
Yes, sir.
Yeah. Butanoic acid, see here, it is a typical hydroxyl group. And no need to get confused whether it is a hydroxyl group of an acid or an alcohol. Because already I mentioned, only in case of an acid, you will get OH group about 3000. And that too because of the extensive hydrogen bonding. Because of extensive hydrogen bonding, you will get OH group around 3000. Somebody was asking what will happen when you go for quantitative analysis. Here lies the problem. When the OH group is coming over here, it is very difficult to identify whether the compound is aliphatic or aromatic. Because the aliphatic and aromatic CH groups comes in this region. So by looking into the CH stretching alone, you cannot confirm whether it is aliphatic or aromatic. So for confirming that, you have to look into this region of the spectrum. You can see that comparatively, this portion is very neat. You will get a lot of scribblings here, rather to say, between 1585 to 1600 and 1400 to 500, if it was aromatic in nature. But here it is comparatively neat. So it rejects all the possibilities for the compound to be aromatic in nature. And see the very strong band that you get here, 1500, 1600, 1700. So around 1007, it is less than 1715. Why? Because of hydrogen bonding, you will get for an acid a peak below 1715. You will get it below 175. So all this tells that it has to be an aliphatic acid. It's an aliphatic acid. Congratulations to Mr. Varma for answering this particular question.
Yes, sir.
Yeah. Really nice. Really nice. And anybody is having the doubts, they can please share it. Maybe the technical expert can tell me the chat if any questions are obtained with respect to this question so that it can be answered. Then all the other supporting bands I put here, OH band, CO stretch, those things are added to this. Any questions are there, madam, in the chat regarding this?
No, sir.
Okay.
No.
Can I go for the next one? Here again.
Yes.
Tell about this. Again, it's a photograph of the compound. Anybody is coming with the answer?
Methyl benzoate.
Yeah.
Santosh
Okay.
Patnaik, maybe.
Okay, fine. Nice attempt. Nice attempt. Very good. Excellent. I will give some clues. I think I will
Yes,
give
sir.
some clues. I
Yeah,
think
yeah,
that
please.
will see this peak first zone. See this peak
Somebody has
second
given
zone.
acetone.
Acetone.
Kalyan
Okay.
Varma.
Okay. This peak you should not miss it. This peak you should definitely not miss it. I will say. You should take into account the spectrum you are getting here, the type of the band that you are getting here, and you will get the answer. And again, this peak, you should not miss this peak. Very important peak. And now I have given you the answer. I did not spot it out, but I have told you the answer now.
So 2 of them given 7th compound.
Excellent, madam. Very nice.
3. Everybody is giving now.
Next time you can call them for the presentation, madam.
Oh, sir, we got 4, 5 members.
Very nice. I'm so happy. I'm so happy.
Sushmita, Pooja Deshmukh,
Very nice.
Shruti, Dr. Harshavardhan,
Oh, great.
Preeti, Lakshmi.
Can somebody come out with the answer, madam? Is it possible for somebody to come out with the answer for that? Is it possible for you to unmute anybody so that they come with the answer for that?
It's possible. Actually, participants have to show interest to talk to us.
So maybe I will just announce that in the chat, if you feel like telling the answer, please put in the chat so that we can unmute and you can interact with the rest of the crowd. So that so if somebody, so putting the right answer is very good, very nice, but much we will appreciate if somebody who is putting the right answer come out with proper claim for that. Why you have put that? That will make the session more interesting. So please put in the chat next time if you want to comment on it.
I request Sridhar, you please unmute to those participants. If anybody is interested, they will express their views to us.
Madam, unmuted, madam. Pooja Deshmukh, Sushmita.
Yeah.
Durga Bhavani.
Yeah.
Rushi Sheikh. Yeah, unmuted all these people.
We are ready to appreciate your efforts. You please, we have given access to interact with the speaker directly. Please
you can just say that. You can just say the answer. You can just say why you have opted that. If anybody.
Sir, they are showing interest to chat only. Yeah, already Kirtana, we have given the access to you. Please talk to the speaker. They have given the explanation in the chat.
Sir, at 3,200 above, we are having the OH stretch. And along with that, at 2,260, we are having acetylenic stretch. So based on that, I have come to the conclusion that it might be propargyl alcohol.
Okay. How do you come to the conclusion that it's not an aromatic portion? There is no aromatic portion.
We don't have any peak, no, sir. For
excellent. Excellent. 1,585 to 1,600, you don't get a peak. Comparatively, the CH bending vibrations you cannot see. And can you see this particular peak? Very important peak. Please don't miss this peak also. This peak is very, very important. In compounds, ethers, carboxylic acids, alcohols, wherever you are having a C single bond O, you can definitely see this particular peak. And I think in the base values I have given you, C single bond O will be equal to 1100. The base value is around 1100. So this is for that C single bond O. Never miss this peak also. Sometimes it will be very difficult for you to identify a compound. So many functional groups will be there. Sometimes it will be so confusing for us. So every band, wherever possible, you try to, here it's okay. Because you are getting a C triple bond C, you are getting, see the difference between the C triple bond N and C triple bond C here. C triple bond C, it's a sharp peak, but the intensity is less. C triple bond N, in the previous slide, I think you remember that, see the peak that you get here, C triple bond N. It's a very intense peak. Whereas when you come to C triple bond C, the peak length is very less. So this is typical of a C triple bond C. You get an OH group, and she rightly said, you are getting it at a higher wave number, no multiple bands you are getting. So definitely the answer is propargyl alcohol. Excellent. Very nice. Very nice. Very nice interaction. So I'll go for the next one. Yes. This, I think it should be very clear to you. Yeah. It is a very, it should convey the information. Yeah.
Yes, sir.
మేడం కీర్తన నిన్న కూడా క్వశ్చన్ అవర్ లేకపోయినా తనే ఆన్సర్స్ చెప్పింది మేడం మెజారిటీ చాట్ బాక్స్లోనే
Any answers? Any answers came, madam? Madam, any answers came?
Yeah,
Yes, sir.
just now unmuted my mic. Okay. Number 8, sir.
Number
Compound
8.
Compound 8.
Great. Who is that person, madam? Who is that person?
Lakshmi Deepika.
Can you just unmute her, if possible?
Lakshmi Deepika. And somebody has given methyl benzoate.
Can I go for the person who has told benzaldehyde?
Yeah. I request Sridhar, please unmute Lakshmi Deepika. Sir, so many members have given the answer. Not only Lakshmi Deepika, Vasantamruta, Santo.
What is the compound they have interpreted, madam?
Vasantamruta and Lakshmi Deepika, compound 8.
Excellent, madam. Very nice. Very nice.
Santosh Patnaik, K. Kirtana mentioned methyl benzoate.
Okay. I will give the answer for that also.
Okay. Mr. Dayanand have given again compound 8.
So I think the controversy is between whether it is an aldehyde or an ester. Am I right, madam?
Yes,
Am I right? The controversy is regarding that. Okay, fine. Yeah. Obviously, here, what you should know is this clearly tells that there is no bands that you can see in the first zone. But in the second zone, there are two types of bands, above 3000 and below 3000. You have two types of bands, which clearly tells that both aliphatic and aromatic portions are there. Aliphatic and aromatic are there. So we can just neglect all those compounds where only aliphatic or only acetone you can rule out. Isopropyl alcohol you can rule out. Propargyl alcohol you can rule out. Acetophenone, yes, you can keep in mind. Methyl benzoate, then benzaldehyde. Because all the other places, if you take either they are only aliphatic or only aromatic. So you have to take into account only those compounds where both aliphatic and aromatic. Now, again, what about this two peaks? Where do you get that? See the position of the peaks. This is 2000. Where do you get that peak? 2000, yeah, 2000, 100, 200, 300, 400, 500, 600, 700. You are getting it around 2700 and 2900. So when you get peaks very much away from 3000, when you get the peaks very much away from 3000, that is 2695 to 2830. I'll repeat once again, 2695 to 2830, or around 2750 and 250. You are getting two peaks, almost of equal intensity. You are getting a doublet. It clearly tells it is a Fermi resonance. It is a Fermi resonance. You cannot neglect this band because it is the only diagnostic band for an aldehyde. An aldehyde only will show like this type of peaks. Two characteristics. One, it will be a doublet and it will be away from 3000. It will be below 3000 but away from it. 2850 and 2750, near about that. And other supporting evidences, you can add it. It is a mono substituted, so you are getting two peaks around 700 and 750. Then the pattern of the bands that you are getting. So obviously the answer is benzaldehyde. Congratulations to all who said benzaldehyde. Really nice, really nice.
Yeah.
And it is not methyl benzoate because of the presence of the CS3 group. It should have come closer to 3000. And not only that, this aldehydic Fermi resonance is so visible. So because of that, we are confirming that it is benzaldehyde and not methyl benzoate. But of course, predicting that it is a carbonyl group and coming close to the answer is really appreciated. Really nice for all who attempted.
Sir, one participant has mentioned that 9.
That is what, madam, methyl benzoate. That only I was telling. It cannot be methyl benzoate because there is good evidence to say that it is an aldehyde. And if it was methyl benzoate, the methyl group should have given a stretching close to 3000. Here you should have got that. The typical pattern is not there. And this pattern clearly tells that it is an aldehyde. Fermi resonance. Very clearly evident. That is the reason why we are not taking. But I again want to appreciate the person who had told methyl benzoate because he is close to the answer. He has taken efforts. Can I go to the next one? Yeah. This you need to tell only the compound name. A, B, C, D, E or F. That's all. They need to mention only the compound name A, B, C, D, E or F. That's all. And somebody can tell the reason, it will be highly appreciated. Madam, any answers?
B, sir. B.
B.
B and D.
B and D. Okay, okay,
yeah.
okay. Can you just unmute
Yes.
them if possible? Unmute them if possible. If
Sure,
possible, madam.
Yes, sir. Yes, sir. Always, sir. And
Yeah.
sir, meanwhile, one of participants are requesting give a little bit explanation about Fermi resonance. I think we
Fermi
have
resonance.
covered.
Definitely,
Oh,
madam.
yeah.
Very nice. Very nice. I will.
Yeah. Meanwhile.
Definitely. Can I go back to that slide, madam? I'll just go back to that.
Yes, sir. Yeah. We got B, D, and F, sir. Answers.
Okay, madam. Right. Just I will
Meanwhile,
take up
I
that.
request Sridhar, please unmute to those participants. Unmute Dr. Harshavardhan, Ranjan, Kalyan Verma.
Madam, this one only, no? Fermi resonance. Somebody was asking about Fermi resonance. Am I right, madam?
Yes, sir. Yeah. Need a little bit explanation.
Yeah, definitely.
Santosh
See,
Patnaik.
what you need to understand here is, here there is a carbon-hydrogen stretching vibrational frequency. Okay, that carbon-hydrogen stretching vibrational frequency will occur at 2720 centimeter inverse. So CH stretching will occur at 2720. Along with that, the CH bending vibration is also there. Hydrogen, carbon, oxygen. The CH will show bending vibration also. This bending vibration will occur at 1400. Previously, we explained about overtone. So what is an overtone? If a particular bond is vibrating with a particular frequency, double this frequency, if an IR radiation comes, it can absorb that. Suppose you have a bond, it vibrates with a frequency, and if double the frequency, if that IR radiation, some IR radiation is coming with double, it can absorb even that also. And it will show as a band, which you call it as an overtone band. But in usual circumstances, the intensity of this band will be very less. You cannot detect it. So let me come back to our example. In this case, what happens is, as I told before, CH bending vibration will occur at 1400 and overtone will be double of this, 2800. But here the advantage that you get is, the CH stretching will absorb at 2720. And CH bending will, first overtone of the CH band will occur at 2800. So what happens here, since the first overtone of the CH bend and the CH stretching frequency, they are closer to each other, usually this overtone will not be seen. But in this case, the overtone will be seen because it is close to the stretching frequency. So what will happen? This will absorb the energy from this CH, or you use the term, the overtone will steal the intensity from stretching frequency. The overtone will steal the intensity from fundamental band. So this is a fundamental band, this is an overtone band. The overtone band will steal the intensity from fundamental band. That will also be showing up in the spectrum. And this is what we call it as Fermi resonance. And it is the one and the only diagnostic band that is very much distinguishable diagnostic band for identifying aldehyde. I hope it's clear. The Fermi resonance is clear to you.
Yes.
The person who has asked, I think it is clear. Am I right, madam?
Yes, sir.
Okay.
Yeah.
So let me go to that particular problem, what we are trying to solve. Madam, in between, anybody is asking the doubts, please feel free to clarify with me, madam. So I'll be clearing them. No problem.
Sir, sure.
I think it was this spectrum. No. This spectrum. This is the answer.
They have given B.
It is actually C. C. It is not B. It is not B. It's C. The reason.
Yeah, we got answer C also, sir, from Kirtana. So Kirtana, soon he will receive one surprise gift.
Definitely, madam. Definitely. All those who attempted, they really deserve a lot of applause because they are using their brain to work on it. That is really appreciated. That is really appreciated. That shows their interest. That is enough to take them a long way in this spectroscopic analysis, irrespective of the type of the technique. And why it is not B? Because you should look in for a C double bond O group. C double bond O should give a peak between 1700. You are not getting that. 1500, 600, 1700. You are not getting any peaks in this range. Typically for a ketone, C double bond O, you should be getting a peak around 1700. You are not getting it. That is why you are rejecting it. You are rejecting this also. Okay. This you can straight away reject because this contains only aliphatic portion. Here you have both aliphatic as well as aromatic. So whatever compound you want to interpret, it can be aliphatic and aromatic. But here the problem is it is not aromatic, it is only an alkenic because you are not getting multiple bands between 1585 to 1600. A single band is there, 1640 to 1667. 1640 to 1667, you are getting a single band telling that it is a C double bond C. And you are not getting other bands like 1585 to 1600 and all. So it cannot be an aromatic. Not only that, it's a C double bond O is also not there. So the only possibility is this one. Only possibility is this one. That is one. Can I go for the next one, madam?
Yes, sir.
Madam, when you want me to stop, you can tell me. No problem.
Yeah, with this we will conclude it, sir.
Okay,
already the 1:30.
Okay.
So,
Okay. Right. So, can somebody interpret this compound? Any answers are coming?
F.
What is it, madam? F.
F.
Okay. Why it is F? Any idea about that? The person who has told?
What they mentioned?
Any other answers it's coming? Any other answers, madam?
A. They meant Santosh
Any other answers?
Patnaik. A, sir. A.
Only two answers, madam? Only two answers?
Yeah, A and D. One more person mentioned D.
D. Okay. Any other answers?
B. Lakshmi Deepika.
Okay.
A, B, D, sir, and bromine they mentioned.
A, B, D, madam. A, B, D.
Yeah.
Okay. So let me take up the B first. Okay. B if I'm taking. So I will start with this. All those who have responded, you can listen to me now. So if you take B, here, what is that you can see? Aliphatic and aromatic portion. It has to be having an aliphatic and aromatic CH stretching in the ring, in the spectrum. You closely analyze the spectrum. If it is aromatic, you should be getting the peak above 3000. No, you should be getting a peak. Is it there? It is not there. So it cannot be an aromatic compound. So the probability of B can be ruled out.
Okay.
I hope I'm clear.
Yeah.
There is no peak above 3000, so it cannot be this. Not only that, you see multiple vibrations. Comparatively, it is a very neat peak spectrum that you're having. No multiple vibrations. So all this tells that it cannot be B at all. Of course, there is a C double bond O. That is a very positive observation. Very good. But it cannot be B. D.
Sir.
Please tell me.
Few of them given F.
Few of them given F. Yeah. I will come to that also, madam. I will come to that. Okay. And I think somebody has put D also, no, madam? D also there.
Yeah.
D, when you say, absolutely, your observation is correct. It is an aliphatic one. Of course, it can be aliphatic, alicyclic. Your observation is very correct. But how will you account for this particular peak? How you are going to accept this? 1500, 1600, 1700. 1700, when you are getting a peak, you cannot neglect this peak. It definitely indicates a C double bond O group. See the intensity of that peak. See how intensely this particular peak is absorbing. I told you, when you take an IR spectrum, the first group that you should be looking in for is a C double bond. You are getting this, you are getting aliphatic. So invariably, somebody is telling F. It's, of course, it should have been a correct answer provided you got this CH in the spectrum. You see 2850 and 2750, where does it come? 2000, 2100, 200, 300, 400, 500, 600, 700, 700 and 800. You just closely analyze this portion. 2700 to 2800, no peaks at all. Fermi resonance is not there. You are not getting a doublet at all. So it tells that also. It cannot be an aldehyde because Fermi resonance is not observed here. So the only possibility. Congratulations to the person who conveyed that it is compound A.
Syed Amina.
Yeah. It's correct. Excellent. And again, congrats to all those who have put the other answers also, because they are in the correct in the correct way only.
At least trying to interpret.
Very nice, madam. So,
sir, shall we conclude, sir?
Yeah, definitely, madam. It's up to you, madam. No problem. I have got plenty of spectrums, but I think all may be hungry, and so maybe some other session we will have some other day where I can have more about IR spectrum. So with this, I can.
Yes.
No.
With this, with this,
I request, madam, please give the conclusion remarks.
Sure. With this, we have come to an end of this session. Thank you so much, sir, for today session. Your amazing lecture on IR covers the in-depth knowledge of spectral interpretation. So really amazing, sir. It's more and more informative and useful for characterization of compounds in the simplest way. Sir has creating effective visuals, analogies, and examples to reinforce the main points. Generally, we used to follow hunting and pecking method, means comparing a spectrum and frequency table line by line, which is a time-consuming strategy for interpreting the IR spectra. The people who have no plan will always follow the hunt and peck method. So by attending the today's session, you can save yourself a lot of time and confusion. Sir has boosted up our confidence and energy levels to identify the functional groups from IR spectra. Sir, thank you so much, sir, for your wonderful lecture and spent a valuable time, enormous time with us for your patience to clarify the doubts, our doubts. Really, it's amazing, sir.
And madam, before concluding, I would like to put once again my screen, because somebody was asking for my contact mail ID. So I will just put the last slide also. Just a minute.
Sir.
And with that, I will conclude it, madam. Just a minute.
Yes, sir. I hope everyone had acquired knowledge through this session. It was glad to see you. Your active participation during the interactive session. I take this opportunity to thank today's speaker and as well as the participants.
So, thank you, madam. Thank you for giving me this great opportunity where I could interact with a lot of participants. It was, in fact, a very fruitful session, what I had with the, and I'm really satisfied with the responses that were coming from the part of the participants too. And so I would like to conclude stating that don't depend only on infrared spectroscopy to find out the structure of a compound, because it has got its own limitations. And some of the signals can be really ambiguous. By our discussion, I think quite often the participants would have seen difficult to interpret, because some signals they expected some frequency and something else is coming. So always you should depend upon more number of diagnostic bands. Don't see a single peak and confirm that this could be the functional group. Yes. But definitely the negative informations also give you a lot of informations. the negative information gives you a lot of information. That's the way I would like to put it. Because when you say it is a ketone, it definitely tells that there is no OH band, there is no amide band, there is no amine band. So that negative information gives you also very positive information about the probable type of functional group that can be present. So even a very simple molecule can give rise to a very complicated spectrum. And advantage has to be taken use of this complexity while trying to interpret the structure of an organic compound while comparing the spectrum of an unknown organic compound with that of an authentic sample. And a peak by peak correlation is an excellent evidence of the identity. So thank you, Professor Dr. Sunita Madam, for giving me this opportunity to interact with a wide crowd. And it is really the first experience for me in having a webinar through the net and
online.
And I'm so happy that we did not have any interruptions in between. Net really helped us. Okay,
yes,
so
sir.
Thank you very much, madam. Thank you. And my mail ID is here. So anybody who wants to put across to me any doubts regarding this, whatever informations I have, I'll be happy to share with them. And thank you very much, madam. Thank you very much.
Thank you so much, sir. I thank today co-convener Professor Nagaraju garu and our technical team members who have supported to make this event as a grand success. I request all the participants kindly submit your feedback before leaving this program. Thank you one and all. Now I am going to end this program. Thank you, sir. Once
Thank you, madam. Thank you very much. And thanks to all the other doctors also, Dr. Nagaraju, sir.
Co-conveners.
Thank you.
Thank you very much, sir. Thank you very much. Thank you all the participants for your patient listening to this particular presentation. Thank you very much.
We have learned so much from you, sir, today's session.
No, madam. I am also in the learning process, because the reason when the participants interact, I think in that way, and that is what. Thank you very much. Thank you very much.
Yes, sir. Yeah. Thank you all.